Hi, everyone, and welcome to the AP Calculus AB Finale Cram. You're about to go through 5 hours of intensive AP Calculus AB review. And I'm here for now for the next hour. Jamal will be here later. We're really excited to be here with you today. Just to something to get us started. The chat and the Q&A are usually on. They're not on in Vimeo tonight. They are on your Fiveable page, where Pooja and JP are helping out with your questions. And they've got access to me if you really need something. But I just want to start by welcoming you here. Thanks for coming out. Hope you guys enjoy the next 5 hours. All right, so just a reminder that this stream is being recorded. It might appear on our website, YouTube, or other public channels. So make sure that if you're writing something in the discussion boards, that you are okay with your name being displayed and are happy with that. Awesome. So I just want to see how we're doing tonight. Going to open a poll and just ask, are you guys ready to cram? Are you ready? And if you just showed up and you're getting your energy, that's totally fine. We're here for 5 hours. We'll get you there. You know, I'm ready. I've got my water bottle here ready to cram. All right. Awesome. Thanks for your responses. It's great to know there's so many of you out there watching. I know that in a minute, we're going to have Amanda come on, and she's going to just give you a little introduction to our cram tonight, and then we'll get started after that. So Amanda, whenever you're ready, feel free to take.
All right. I'm so excited to be live. I don't get to do the live streams as much as I used to in the past, but my name is Amanda. I'm one of the co-founders and CEO of Fiveable. I've been building Fiveable since the AP exams of 2018, which feels like an era ago. I'm super excited for you all tonight to study with Megan and Jamal for calculus. I know this is a super stressful time for you, but you really do got this. And these next 5 hours, you're going to hit every single concept, make sure that you understand it. And one thing that you can keep in mind is that you can always ask questions in the discussion thread, and our TAs will answer them for you. So there's no reason to be stressed. We got you. The second thing I want to let you know about is that if you chat on the chat bot, if you have any tech issues or questions about your past or anything like that, you can access one of our awesome success support team, and they will help you navigate that. But make sure you don't post those tech questions on the discussion threads, because the TAs are focused on the content. Okay, last thing, I really want to hype this up because this is like a really awesome opportunity for you. You have a chance to, we're actually going to be giving away $100 for one student today that does the best social media entry. So all you need to do, you got 5 hours. So at some point tonight, post on TikTok, on Twitter, or on Instagram, something about your cram experience. It could be showing what your setup looks like, showing what you feel like, posting some sort of, way to kind of relate, right? Like we see it and we're like, that is so accurate of what this cram season feels like. So post something on one of those channels and use that hashtag #YesWeCram and with Fiveable. Make sure you follow us because we're going to DM the winner. That's $100. That pays for your AP exam. We will send you that on like Venmo or Cash App, whatever you want. So like I said, post it before the cram ends. We're going to pick the best ones later tonight. I really want to see some calc winners out there because I know y'all got some good calc related memes. Like you're going through it right now. So post it somewhere on social so we can see that. If you ever need anything from me, I'm always around. I'll be hanging out in Discord a little bit tonight. I unfortunately don't know anything about calculus, so I won't be able to help you there. But I will be able to give you pep talks whenever you need it. So if you need someone to just like give you that last minute boost, let me know. Just tag me in Discord and I'll come through. So I'll kick it back to Megan to hand it off to really start the fun tonight. So have fun, y'all, and I will see you soon.
Yeah. All right, it should be me now. Awesome. That camera's for later. It got a little confused which one I wanted to look at. But thank you, Amanda. So excited to see you all here. And let's get started. I'm going to share my screen and we're going to jump right in. Okay, so same old setup just to start here. It's going to be me and Jamal tonight, which will be fun. We'll be switching off. And let me give you a little preview of what the night's going to look like. All right, so from 5 to 6, you've got me with some multiple choice questions, continuity, differentiability, particle motion, related rates, like implicit differentiation, and graphical analysis. You know, that's a long list. I'm not going to read through all of it because I want to make sure we're spending time doing calculus. But this is everything that we're going to be doing as we go. You may have seen it already. We've got Jamal coming up the next hour with a few more multiple choice questions from the kind of back half of the units. And then I was told by JP, we've got a lot of questions on rate in, rate out. We are going to review that with me from 7 to 8:30. And then from 8:30 to 10, Jamal's going to finish it off with a few more questions from free response and some common pitfalls or common mistakes to avoid on exam day. So we've got a long night ahead of us. We're excited to be here with you. One quick reminder to those of you who are in BC, your stream starts at, well, I wrote 7:30. That's Eastern time. That's the time that I am in right now. So Pooja and JP know this. They've got the link to the stream ready to go when it's time for you to switch over. Of course, you're welcome to stay here if you would like, but I'm sure BC would probably be more helpful for you to head on over there with Elizabeth whenever that starts. Remember, you can always go back and watch this later if you want to. All right, so let's jump right into our topics. Like I said before, these are the topics we're going to be reviewing. I'm going to give you a multiple choice question, let you have a few seconds to think about it. We'll take a poll, and then we'll go over see where we are if we want to go over it in more depth. So first, we're going into limits, continuity, and differentiability. So hopefully we're all really good with this by now. How do we know if a function is continuous at x equals c? Well, 3 things have to be true. F of c has to exist. The limit as x approaches c of f of x also has to exist. That means from the left and right has to exist. And that limit has to also equal f of c. As long as these 3 things are true, then it is continuous at this point, f of c. And then we've got this other thing we have to be able to prove, and that's differentiability. So with differentiability, that means a couple of things. The function is continuous, right? We know that this is the definition. The limit from the left equals the limit from the right equals f of a when a is plugged in. But also, the slope from the left equals the slope from the right. So that's the extra thing that differentiability brings in there. Okay, we've got to be able to show that also the slopes are equal, not only that it's continuous. And then another really important thing to remember when it comes to this topic, a function that is differentiable is definitely continuous, but if a function is continuous, it may not necessarily be differentiable. And again, this should be something that you guys have in your head and that you know of, that if you see differentiability, you know that means continuous. If you see continuous, that doesn't necessarily mean it's differentiable. All right, let's jump into our first question. We've got a differentiable function. We're told it's differentiable, but we've got some letters in here instead of where some constants should be. And we need to find a plus b. We've got a piecewise function where it follows ax squared plus 15 when x is less than or equal to 3, and then follows natural log of x minus 2 plus b of x when x is greater than 3. So we've got to find a plus b. All right, I know that you guys might not have an answer quickly, right? We need to go through this a little bit, so I'm not going to post the poll yet. I'm going to go through this. Feel free to go through at your own speed as we go. But we've got to prove a couple of things. So if we know it's differentiable, that means we know it has to be continuous and their derivative from the left and right have to be equal. So let's take a look at how we can prove that. All right, so now you should see this computer screen, well, document camera screen. And let's think about this function. This is our first part. And what you need to think about now is that, well, if we have two unknowns, we're missing B and A, and we need to find A plus B. If you learned system of equations in Algebra 2, that means that we need two different sets of equations in order to be able to find A and B here. So let's see, what do we know? Well, we know it's differentiable, which means we know it's continuous. So they have to be the same at 3. So when x is 3, that means that ax squared plus 15 has to be equal to the natural log of x minus 2 plus bx. And so I'm just going to go ahead and plug 3 in there because it's only at x equals 3 that we care about. And then this would, I'll just make this 3b. 9a plus 15 equals natural log of 1. Well, isn't that nice? The first time I practiced this question, I accidentally put a plus sign there and had 5. So it's like, oh, this is a lot harder than it seems like it should be. Make sure you're checking what your signs should be because that might make a big difference for you. Okay, so we've got this now, which we can simplify a little bit more since natural log of 1 is 0. And now we've got one equation with a and b in it. This we got from knowing that it's continuous. But we also know it's differentiable. So if it's differentiable, that means their derivatives have to be equal. So that means, well, my derivative of ax squared, where a is a constant, is going to be 2ax, and then 15 will go to 0. And then my derivative of my second one will be 1 over x minus 2 plus b, right? The derivative of bx will just be b, whatever our constant is. Now we've got two formulas here. Now we can use those, use substitution. This is where the algebra part comes in handy. Make sure we're using substitution to, or elimination if you like that, but I'm partial to substitution, I think. Okay, I'm going to solve for b here. Let's see, I'm going to use this one, solve for b. 2a times 3 equals 1 over 3 minus 2 plus b. 6a equals, this is just going to be 1 plus b, subtract 1. Okay, so now we've got b is 6a minus 1. I can use this, put this right in here for b, and solve for a. Hopefully you guys are following along. Please let me know, Pooja and JP, if you can let me know if there's any lag or anything I need to know. I've got my phone here in case you need to contact me. All right, let's keep solving. I'm going to subtract 9a to the side. 18 equals 9a, and so we're going to get a equals 2. Okay, and then don't make more work for yourself by going all the way back here and solving for a. You've got a now, and you've got b. b equals 6 times 2 minus 1. 12 minus 1, we get b is 11. Now don't forget that we need to look back and make sure we know what the question is asking. So I'm going to open the poll now. All right, let's see. I've got to, hang on, I forgot to close this one, so hang on. Let me make sure to close this one now and open the next poll. What is a plus b? All right, we've got 2, 13, 9, or 11. Well, we know that a is 2. We know that b is 11. What we want, though, is what is A plus B. So yes, 96% of you here, we've got 13 as the correct answer, and that is correct. Good work. All right, awesome. That is a continuity problem for you with some differentiability in there as well. Let's go back over here. We got 13 as an answer. Looks great. And if you want to see more of this, you can check out the Unit 2 cram. So if you're feeling like, oh, I really need more practice with that, you can go over and look at our Unit 2 cram. All right, great work with that one. Let's go on to the next. This next question is about particle motion. And I just want to make sure we've got the connection here between position, velocity, and acceleration. We know that velocity is the derivative of position. Acceleration is the second derivative of position, or the first derivative of velocity. And we also know that velocity has a direction. And so if we don't want the direction and all we care about is the speed, then we take the absolute value of the velocity. We might not need all of this in the next question, but let's go ahead and start and see how it goes. All right, we've got a question here from the 2012 AP practice exam. So t is greater than or equal to 0. There's a particle moving along the x-axis. That's given by x of t, which is a lot of times what they call the position. They use x to represent position. Sine of t minus cosine of t. What is the acceleration of the particle at the point where the velocity is first equal to 0? Again, make sure you're looking for clues here of things that might need to make your answer more specific, right? Velocity first being equal to 0 might be different from when all of the times it could equal 0. All right, so we've got 4 options here. It originally had 5 options. There was a fifth option, but polls only gives 4 options, so I took out a 5th option. All right, so let's take a look. What do we need here? We need to find the acceleration, but it says where the velocity is first equal to 0, and all we have here is position. So we need to be able to go from position to velocity to acceleration and use all 3 of those. And we've got sine t minus cosine t. So let's take a look at how we would do that. I'm going to go to a fresh piece of paper. And again, I'm going to do the problem out most of the way and then start a poll. Okay, so we've got sine t minus cosine t. And we want velocity, and we want acceleration. And we know that each of these going down, I'm just taking the derivative one more time each time. So the derivative of sine is cosine. The derivative of cosine is negative sine, so this is going to end up being plus sine. And then one more time for acceleration, negative sine. Ooh. Negative sine plus cosine. So each of these is just a little bit different. Okay, so now we're looking for when v of t is equal to 0, but then it says first equal to 0. So we're looking for when it's first equal to 0. So we've got v of t here, cosine of t plus sine of t. And I know that if I'm just adding these two, I'm going to need them to have the same value, but one of them needs to be negative. Okay, so how do I think about that? Well, this is where it really comes in handy to make sure you have your unit circle. Make sure that you know your unit circle and some of those quick values. I know that cosine of t and sine of t, they are both root 2 over 2 whenever we have an angle that's pi over 4 or a multiple of that. This is 3 pi over 4. This will be 5 pi over 4. And I believe this is 7 pi over 4. And I know that these are all the times when I get root 2 over 2, root 2 over 2, them to be the same. Okay, and so I want the first time it's going to equal 0. Well, I need one of them to have a negative sign. They have opposite signs here and here. So if this is 0 and we go counterclockwise how we follow it, this is going to be the first time when t equals 3 pi over 4 will be the first time velocity equals 0, because we've got cosine of 3 pi over 4 plus sine of 3 pi over 4. This will be negative root 2 over 2 plus root 2 over 2, because we're in the second quadrant, which is 0. All right, but remember, this is not what we were asked for. We were asked to then go back and find the acceleration at this time. So now we've got to think about finding a of 3 pi over 4. So we're going to have negative sine of 3 pi over 4 plus cosine of 3 pi over 4. You guys still see that? Yeah. And I think now I'm going to go back over and open up the poll and see what you guys have. I had to write out these answers in kind of a strange way because it's hard to write square root of 2. But here is the poll. What is the acceleration when the particle is equal to 0? Is it the negative square root of 2, negative 1, 0, or 1? Go click back over here. You can still see the poll, but you can take a look at what we were doing. All right, we're a little bit more split on this one, so why don't we finish this off together? So negative sine of 3 pi over 4. Well, the sine of 3 pi over 4 we have right here is positive root 2 over 2. So we're going to have negative root 2 over 2 plus cosine of 3 pi over 4. We also have that right here. That's negative root 2 over 2. When we add those together, we get negative 2 root 2 over 2, which simplifies to just negative square root of 2. So A is the correct answer, which we've got 63% answered that. So awesome. Good work, you guys. Negative square root of 2 is the correct answer. Again, just so you know, Pooja and JP are, I'm sure, doing an awesome job in the chat that I cannot see. But make sure you're asking your questions to them there, and feel free to add anything they will answer. If they can't answer it right during the stream, we can go into Discord. Just make sure we are here to answer any of your questions, as many as we can. All right, good work with that one. We're ready to go on to the next. Okay, again, if you want more practice with this, Jamal just did a stream on it as a free response question stream. And that was on April 26th. So it was just called the free response review. And it happened on April 26th. So you can go back and look at that if you're looking for more questions about this. And then just another thing to freshen up on with this is speeding up versus slowing down. So if positive velocity is moving to the right, negative velocity is moving to the left. If your velocity and your acceleration have the same sign, doesn't matter if they're positive or negative, that means your particle is speeding up, as long as they have the same sign. If they have opposite signs, it does not matter which is positive and which is negative. If they have opposite signs, then it's going to be slowing down. Just wanted to make sure I reviewed that with you guys going into the exam, because that's not something I have a question on here in these multiple choice. Okay, the next topic we're going to go into is a related rate. It's a little bit of a longer question in terms of reading, so it'll take us a little bit more time here, but we got this. We've got the volume of a cone of radius r and height h, given by this formula here. This is just the volume for a cone. If the radius and the height both increase at a constant rate, so radius and height both increasing at a constant rate of 1/3 centimeter per second, at what rate in cubic centimeters per second is the volume increasing when the height is 6 centimeters and the radius is 3 centimeters? Okay. We've got some options here to show you. 1/3 pi, 6 pi, 5 pi, and 12 pi. So we think pi is going to be in there somehow. This is a little bit different from what you might see on a free response question with a related rate, because this one says the radius and the height are both increasing at a constant rate. So we've got the derivative of the radius and we've got the derivative of the height, and they are the same. So let's take a look at how we simplify this. All right, I'm going to go over to here, and I'm just going to start with taking the derivative of our volume of a cone formula. Okay. Most of the time when you're doing a free response question with volume of a cone, you guys may have seen some in the past. It might be that you don't know anything about R, and that R is going to be something that you have to write in terms of H. In this case, in our problem, we were told dr dt and dh dt, that they are the same and that they're both 1/3. Okay, so we've got both of them. So we're just going to take the derivative of this right from the start. And we can't forget, we've got r squared and h. That's going to be a product rule in there. And we're looking for the derivative of the volume. So 1/3 pi is our constant. That's not going to change. Here we've got to look at using product rule. So the way I talk it out in my head is I say first. So first is r squared times the derivative of the second. The second is h, so dh dt, plus the second, h, times the derivative of the first, which is going to be 2r dr dt. All right, we've got our derivative here. We know this is 1/3. Do we have the other information we need for r and h? I believe we do. We know the height is 6 centimeters and the radius is 3. So we know h equals 6, r equals 3. From here, this is really just a lot of algebra. It's already solved for dv dt. I'll do some of this plugging in with you, and then I'll display our question. So we've got 3 squared. The dt is 1/3. 6 times 2 times r is 3 times 1/3 again. This is this is a question very similar to one from a previous AP exam that I just changed the numbers with. But often if AP is having you do a question like this without a calculator, they are going to give you numbers like this that will very nicely work out to whole numbers. Not always, but most of the time. They're not trying to test your ability to simplify fractions and decimals. They're trying to test your calculus. 6 times 2 is 12, times 3 is 36. So we end up with pi over, I already wrote pi over 3, sorry about that. 3 plus 12. Pi over 3, 15. I've basically given you the answer at this point. Let's just publish that poll and see what you got. What is the rate that the volume is increasing at? You guys are doing awesome, by the way. I really appreciate you joining here today. All right, the votes keep pouring in. I'll give you another second to send in those votes. I know you guys are all over the world tonight, so thanks for joining us, no matter what time it is. I'm over in the Boston area in Massachusetts. Right now it's 5:30. Got 4.5 hours to go here, but you're half an hour in and you're doing great. All right, let's publish these results. So you guys say 5 pi Yes, you are correct. This will simplify to 15 pi over 3, which simplifies to 5 pi. Awesome. Great work with this one. If you are interested in hearing more about this one, check out the Unit 4 cram, where we reviewed related rates. They do appear in multiple choice questions, although you might be more likely to think they'd appear in a free response. On the actual AP exam, they're not likely to make up a full free response. And we're going to go through most of what would be a full free response by the end of this 5 hours we have together. All right, I'm going to go on to the next. Okay, this one is actually not multiple choice. I decided this one, it would be a little bit better if we just did this out, didn't have a set thing to go off of. And this would probably more likely appear in a free response, a piece of a free response question anyway. So we're going to do this one without our options. That's okay. We won't have a poll. But I will give you guys some time to think about this as we go. This was 2004 number 4, and that means number 4 in terms of the free response question. So this was a no calculator free response. So we've got a curve given by this here, x squared plus 4y equals 7 plus 3 times x times y. And your job is to find that second derivative at the point P, 3, 2. And so the previous parts of this question did ask you to find this point, and they also asked you to find the first derivative. So we don't need to worry about the point. I gave you the point, but we are going to need to find this first derivative in order to go to the second derivative and be able to figure out the rest of this problem. And so what we need to figure out is, does the curve have a local maximum, a local minimum, or neither at point P? So we've got a few steps to go through here. All right. So we are starting with x squared plus 4y squared equals 7 plus 3xy. Oh, let me move that down. You guys are doing great, by the way. I'm loving your participation in the polls. Sorry we don't have a poll for this one, but I hope you're following along and writing down the work as we go. And again, sending questions to Pooja and JP in that discussion thread. Okay, so our first step, we want to find the second derivative. But in order to do that, we're going to have to find the first derivative first. So I want to take the derivative with respect to x. And again, this means because we've got y intermingled in here, we've got implicit differentiation. So derivative of x squared, great. That's 2x, not too bad. Plus 4y squared. We use our power rule to get 8y, but we can't forget to multiply by dy dx. That's our implicit. Derivative of 7, 0, because that's just a constant. But this 3xy, we are going to have to simplify. When I see a constant here, I usually just put it outside of parentheses because x times y, again, we're looking at product rule. Made that into an R, so just improvise there. Product rule. So first times derivative of second plus second times derivative of first. I'll just write the 1 here so we know it's here. And now we can simplify to find dy dx. Oh, row equal, sorry, that's a plus. 8y dy over dx. 3x dy over dx. Feel free to go ahead of where I am if you're all set and know where you are. I just want to make sure we're showing this out because this is definitely, you will see a problem that is implicit differentiation where you have to simplify and find the first or second derivative. So I'm going to move this 3y over here because the next step is I want to get dy dx to one side. So I'm going to do 2x. I'm going to move this 3y over. 2x minus 3y equals, and then I'm going to move this 8y dy dx to this side. Okay, so I'm moving this over here. So we get 2x minus 3y equals 3x dy dx minus 8y dy dx. And now, let's see. I want to pull out my dy dx. So I get 2x minus 3y equals dy dx 3x minus 8y. We've almost got it. Awesome. Okay, so we found dy dx. You can still see it, yes. And this is where it's going to get fun. Okay, so we found dy dx. Looks good, but it is a fraction. It is a rational function. And so if we're going to find our second derivative here, the whole point of this question, we're going to need to use quotient rule. All right, so looking to use quotient rule here. Again, I use in my head low d high minus high d low over low low. I'm going to write that out a little more formally here to make sure we've got that definition. G of x times f prime of x minus f of x times g prime of x over g of x squared. Okay, so 3x minus 8y times the derivative of the top, which will be 2 minus 3 dy dx. Okay, don't forget, we're still doing implicit differentiation, 3 dy dx here. Minus 2x minus 3y times the derivative of the bottom, which will be 3 minus 8 dy over dx, all over 3x minus 8y squared. And there we have our second derivative. Oh, sorry, this is a y. Whew. Okay. So now we've got to do something right with this, right? We were told that we have to find at 3, 2, we have to find if it's a maximum, a minimum, or neither. So let's use this. We've got x and y, and we have dy dx. Where is it? Right here, dy dx. So here we go. I'm going to first plug in dy dx. Bear with me here. This is going to be really long on your paper. Make sure you've got a nice full open piece of paper to write this on. 3x minus 8y, 2 minus 3 instead of dy dx. And this is the really important part that you need to remember to do. You've got to plug in dy dx where it was in the function, 2x minus 3y over 3x minus 8y. I know right now you're thinking, oh my gosh, this looks horrible. Why are we doing all of this algebra? Just wait. You'll be pleasantly surprised. 2x minus 3y, 3 minus 8. Okay, and then again, we've got to plug in our dy dx here. If you want to skip this step of rewriting it, sure, you can do that. But for me, it always helps to write out the extra step. It prevents a lot of silly mistakes I do if I'm doing algebra in my head. Okay, so now I've got to use this 3, 2 here. So anytime I see an x, I'm plugging in a 3. Anytime I see a y, I'm plugging in a 2. Okay, so here's where you should start to see, oh, that looks good. 2 times 3 minus 3 times 2. That's nice. Well, this is really nice too. I'm going to finish plugging it in just to make sure we can see that we've got everything plugged in correctly. hopefully you can see that. I know it's not very clear, but in a second you won't care. 8 times 2. Pretend there's a parentheses there. I didn't even leave myself enough space. And then we've got 3 times 3 minus 8 times 2 squared. Okay, so we look at this and we're like, okay, well, 2 times 3 minus 3 times 2, that's just 6 minus 6. This is 0. Where else does it appear? It appears right here. This is 0. This is also 0, but that doesn't even matter because it's being multiplied to this 0. So this whole piece right here is gone. We don't even need it. That is really nice. They had us do all of that out. And now it's just 0, which is fine with me at this point. Okay, so let's just do out this part. So 3 times 3, 9 minus 16. And then this part became 0 times 3, so that's just 0. But we still have this 2 out here. Over. Now, this is going to be also 9 minus 16, but it's squared. Okay. So 9 minus 16, we've got negative 7 times 2 over negative 7 squared. Well, negative 7 over negative 7 squared. We can simplify out one of these 7s. So we get 2 over negative 7. Whew. We got the answer, negative 2 over 7. But the question was, what was our question? We got negative 2 over 7. We did all this math. We found the first derivative. We found the second derivative. We used the point. The question was asking, does the curve have a local maximum, a local minimum, or neither? Actually, I can make that into a poll for you. Let's create another poll. Maximum, minimum, or neither. Get your answers ready. Okay. So in a second, give your answers. Oh, sorry, pressed archive too fast. Let me do that one. Oh, we still got 4 votes in. You guys are fast. I meant to hit share and I hit archive. One more time, you guys. Thanks for bearing with me. I am impressed with you guys that were very fast and able to get your answer in that quickly. Okay, we're going to try this again. Open the poll and show. There we go. Maximum, minimum, or neither. All right, we're somewhat split on this. I'm going to give this another minute to see what we end with. Remember, we're looking at the second derivative. We're looking at the second derivative, and it came out to negative 2 over 7. Move that up for you. Negative 2 over 7. What does that mean when we are talking about a maximum or a minimum? I'm glad we went over the end of this one because we have to look at these results. All right, let's take a look. Okay, so we've got maximum 48%, minimum 39%, and neither. So it's very tempting. It's very tempting when you see a negative value to think that's a minimum. But what does a negative mean in the second derivative? That means concave down, right? Which means your graph has a maximum. All right, make sure you're always interpreting what's happening based on what you're looking at and which function you're looking at. If it's its derivative, its second derivative. So those of you that put maximum, awesome, great work. If you put minimum or neither, make sure you think about that. Hopefully that makes more sense now. Hopefully you're asking questions in that discussion thread. All right, good work with that. Okay. we're going to go now to our next question, and I believe our last topic for my first hour. Let's see. Oh, sorry, one more thing. Check out the Unit 3 cram for more like this. So if you would like more questions like this, make sure to go into the Unit 3 cram. All right, the next question has become increasingly popular. It's about graphical analysis. And here's our first question. So we've got a graph of f, and we're told that it's a differentiable function. And we're also told that h of x equals the integral from 0 to x, okay, 0 to x, of f of t dt. Which of the following is true? When you're given a question like this, you might think, how am I supposed to find h of 6, h prime of 6, and h double prime of 6? You don't, most of the time, for ones like this, you don't actually need to find the exact values, okay? A lot of times, one of these values is going to be positive, one's going to be 0, and one's going to be negative, so you don't even need to know the order of these. I'm going to give one more minute, and I'm actually going to ask you guys to think about this one, and I'm going to put the poll up first, and then we'll go over this one. So give you some time to think about it. You guys are doing great so far. Thanks for tuning in. If you just got here, I'm Megan. Jamal is starting off at 6, so you've got about 13 more minutes with me, and 6 Eastern time, so just the next hour for wherever you are. And he's going to be doing some more multiple choice. The second half will be all some free response questions and some common things to look out for on the exam. All right, I am going to start the poll. Which of the following is true? This poll, I just wrote A, B, C, or D. So which one do you think? A, B, C, or D? We're going to go over it either way, so even if you're not sure, don't worry. What do you think? Give one more minute to respond. Some people are still working, I think, because we've got a few lower votes than usual. Okay. I'm going to give you about 20 more seconds to answer, and then we'll review this question. Okay, so what we've got here is majority thinking that it is A. 49% saying A, so let's check in, see how we're doing. I agree with you. Let's make sure we can convince everyone else here that that's correct. Okay. So I'm just going to draw a sketch of this graph. We don't need the exact thing. We just need a couple key points on it. So we know that this is 6. We've got -2 here, and it dips down here, and then up and over like this. And we know this is f, and we know that h of x equals the integral of f. So what's important here is to know the relationship. All of your answers are in terms of h, but your graph is in terms of f. So the first thing to do is figure out what is this graph in terms of h. Well, if h is the integral of this, that means if we take the derivative of h, we are going to get f of x. So what we're really looking at here, even though they told us it was the graph of f, part of what they're doing here is testing your ability to interpret, because this actually means the derivative of h. So now that's all I'm thinking about. I'm thinking about the fact that I'm looking at the derivative of h here, and 6 is the point where the derivative is 0. So I've got one answer already. I've got h prime of 6. I know that that's 0. Now I also need h of 6. I'm just going to write that one above in h double prime. Okay. So if I want h of 6, I know that means that I'm looking at the integral from 0 to 6 of f of t dt. I don't know what this integral is exactly. I don't have an actual function. But what I do know is that I can also use area, right? If I'm using an integral, that's the same thing as talking about the area, or in this case, above the curve, because it's negative. But that actually helps us a lot, because from 0 to 6, all of the area is under the x-axis, which means this is a negative number. We don't know what this number is, but we know it's negative. Okay, so we don't need any more information right now. So we're just going to leave that as negative and move on to h double prime. Now, again, we're looking at h prime. So we want to think about the relationship between h prime and h double prime. And I know that the relationship between a function and its derivative, if I think of them as a function and its derivative, if this function is increasing, that means this is positive. And if this function is decreasing, that means this is negative. So then I go up here to my graph of h prime. I see that it is increasing, which means that my second derivative is a positive number. Okay, so as I've said here, we don't need the exact numbers. We've got negative, a 0, and a positive. I know that h of 6 is the smallest because it's the only negative. And then I know that h prime of 6 is 0, so that's going to come next. And then the biggest one is h double prime of 6, and that is positive. Make sure you're paying attention to the direction of these signs. I think all of them are going the same way in the question. Yes, all of them are starting with less than. So when I first did this, I thought, okay, I want to write mine in the order that would put them less than so that I can look at it in that way. And A is correct here. Okay, if you want more like this one, Jamal, again, did a stream, a free response question review on April 22nd for more like this. Good work. All right, we have 7 minutes left, and I have one more question for you. So this is perfect timing. And then Jamal's going to be taking over for that next hour. Okay, let's take a look at the next question. This is our last one here. We've got the graph of f prime, the derivative of f. It's that line shown above. We know f of 0 equals 5. What is f of 1? So this is another graphical analysis. It's from 2003 exam. It's number 22. This was a released exam. And yes, even though it was from 2003 and that seems like a long time ago, these are very popular questions. Okay, there's a reason that this was a released exam and that everyone has access to it, because these questions show up. Okay, I think on this one here, I'm going to start us off. Then I'm going to let you try some answers, and then we'll finish it together. So the information that is important to us here. We've got our graph, 1 and 6. And we know f of 0 is 5, and f of 1 we are looking for. So if we're looking at f prime, we know that in order to get to f, we're going to need an integral, right? We're going to need the integral from 0 to 1 of f prime of x dx to get us to f of x. And we know, because of the fundamental theorem of calculus, that the integral from 0 to 1 of f prime is going to be f of 1 minus f of 0. Well, this helps us because f of 1 is what we're looking for, and now f of 1 is right here. So if we can use this and this to solve for f of 1, we'll be able to find our answer. This is where I'm going to stop, let you guys think about how we would find this answer, give you about 2 minutes, and then I'll spend the last 2 minutes wrapping up, and we'll head over to Jamil after that. So let me open this poll. Okay. Okay, we've got almost 100 votes in. Come on, you guys, you got this. We've got still about another minute and 20 seconds. I know Jamil's over there probably getting ready to take over, and excited to be with you guys. Again, we really appreciate you all coming out and working so hard. We know how much you guys have going on, and we're so happy that we can provide you with this extra little boost right for your cram finale, getting ready for the AP exam tomorrow. And if you're not taking it tomorrow, there will be watch parties where you can rewatch these in case you want to spend 5 more hours with calculus. Okay. All right, I'm going to finish this one off with you guys. I'll wait to tell you the results for a minute. So I know I want f of 1. I'm just going to move f of 0 over here, add it to the other side so that I've got f of 1 there by itself. So now I've got f of 0 plus this integral from 0 to 1 of f prime of x dx. And that's going to tell me what f of 1 is. And so this part right here is kind of the part that is easy to forget. You might look at this and say, okay, well, all I have to do is take the area of this shape because it's an integral, and that's all I need. That's not true. You've got to remember that we had a value starting at 0. We can't just use the integral from 0 to 1 because we had something starting at 0. So we've got that 5 plus, and now this part we can just use the area. Area of a triangle is 1/2 base times height. 1/2 times 1 times 6. That will tell us f of 1, which looks like 70% of you got. We end up with 5 plus 1/2 of 6 is 3. And we end with 8. Awesome. All right, great work, you guys. So that's just about the end of my hour. What we did this hour, again, was we went over graphical analysis, implicit differentiation. We did some continuity, differentiability. What else did we do? Let's make sure we've reviewed it all. When we did a related rate and a particle motion. So you've already got all those. And remember, the slides actually tell you what stream you can see it from. Speaking of that, you can see this one from the April 22nd stream. Okay, and next we're going into a few more questions on multiple choice that Jamil is going to start with. Let me just stop sharing for a minute so you can see me and I can say goodbye for now. So you will have Jamil for the next hour, and then it's going to come back to me from 7 to 8:30 and then back to Jamil. So awesome. Pooja and JP, thank you for what you've done so far. Again, everyone keep using those discussion threads. And that's it for my hour. So thank you guys so much. Jamil, you can take over whenever you want, and I'll see you guys again at 7.
My name is Jamal. I'm going to be working with you guys for the next hour. That was Megan who just left us, and I am on, and we're going to continue going to touch as many multiple choice section topics as we can over the next hour. We're going to really focus on some of the more commonly asked questions. But while I'm getting set up and getting my video all set up, I'm going to pull up to see how the first hour went. So if you guys could let me know, how was that first hour? Okay, let me know what you're thinking. All right. Looks like you guys are doing pretty well so far. Here's the results of the poll as we see them here. It looks like you had a good time. Again, my name is Jamal Sadiq. I'm coming tonight from Massachusetts. So if I happen to mention the times, please keep in mind I'll probably do an Eastern time with everything that I say. Okay. Let's see here. All right, so for my first hour this evening, here's what we're going to be focusing on. We're going to be looking at reviewing some quick questions that often appear in multiple choice questions, the topics that you're going to see. We're going to talk a lot about calculus skills, okay? So just these really short skill-related questions that are all over the first 20 or so multiple choice questions. So we're going to do a lot with that this evening. We're going to look at integration by U-Substitution. I know that some of you have been asking for that in the question and answer, so we'll be covering that. We're going to be talking about some properties of integrals, which is always a common question. We see one or two problems on that each year. We're also going to talk and review the average value of a function formula. And the last two things kind of go hand in hand that we'll be doing during this next hour is interpret the meaning of a derivative and interpreting the meaning of an integral. Those used to be primarily free response questions, although over the last 4 years or so, we've been seeing them in the multiple choice and the free response. So I hope you guys are as excited as I am. We're going to get going. We're going to start off with a question that I hope everyone can answer at this point in time. And that's, what is calculus? I ask this question all the time from my students. I ask them, what is calculus? And whenever I ask this question, here are the answers that I usually get. I usually hear derivatives right away. You can't think about calculus without thinking about derivatives. Along with derivatives, integrals goes hand in hand. The question that I like the answer I like to get from a lot of my students is they just say it's hard. Some of them have a hard time, but they work at it and they work hard. That's what you guys are doing here tonight. You're continuing to work hard, and you're going to see some success. You're going to see so the benefits pay off tomorrow. Okay. Another thing I hear all the time is limits. Limits is always very important in calculus. If you ask me, the answer I'm going to give you is calculus is straight up beautiful. Okay, it is a beautiful thing, and I'm going to try to help you find the beauty in it tonight. But the actual answer that we're looking for when we say what is calculus, it's the mathematics of change. That's what it is. It's the tool that allows us to quantify change, to predict change, to really, really get a handle on how things are changing. Okay, but when you ask most people, the answer they give are derivatives, integrals, and limits. Now, what I want to talk to you about for the next however long it takes us is our calculus skills. And what I mean by the calculus skills, I mean the tools that allow us to answer the calculus questions, okay? And those tools are limits, derivatives, and integrals, okay? They're not the end-all, be-all, but they are what are the tools that allow us to do it. So it's kind of like this, if you said, how do you build a house? You wouldn't answer, you get a hammer and a ladder and nails. Those are the tools you need to build that house. And limits, derivatives, and integrals are our tools. So I'm going to put up on the screen real quickly just some samples of these types of problems that are very, very common on the first 20 or so multiple choice questions. And then we're going to go over and make sure that you guys are prepared, because we don't want you to get any of what I call these skills questions wrong. They're the most straightforward questions on the exam, and we want to make sure that you guys get all of those and get the credit you deserve for them. So again, here are some of the examples that we see. These are 3 typical type limit problems, and we're going to go over them all individually, so I'm not going to leave them up very long. But these are the types of limit problems that are just straightforward. Here's a limit. Can you answer this limit? And we'll be going over those in a second. Next up, derivatives, okay? Here are 3 derivative type problems that come from free response type, multiple choice type problems all the time, okay? So we're going to be reviewing these 3. We're going to be making sure that you guys know the rules and the appropriate way to take these derivatives. And then last but not least of the skills are the integrals, okay? So here are 3 samples of integrals that show up on the multiple choice year in, year out, and we're going to make sure that you're ready. You might recognize some U-sub problems in there already. So we're going to go and we're going to be looking at all of these tonight, and then when we wrap this up, we're going to go jump to some more multiple choice questions. So we're going to be moving at a pretty quick pace. JP and Pooja are there answering the questions, so be sure to use them as much as you can, as much as you need to. I'm going to be going through the steps and getting you ready for what you need to know for the exam. So what I'm going to do now is I'm just going to cross over to my tablet, and we're going to just look at doing these problems. So we call this in my classroom, this is an example of a graphical limit, and an algebraic limit. And whenever we have an algebraic limit, the first thing that I think about doing is just substituting in, because sometimes we can get lucky and we can substitute in. So if we substitute into this one, if we take the limit as x goes to 2, we're going to get 2 cubed minus 8 on top. We're going to get 2 squared minus 6 times 2 plus 8 on the bottom. And when we do that, we're going to get 8 minus 8 on the top. On the bottom, we're going to get 4 minus 12 plus 8. And if any of you guys have been, following along this year, you kind of expect it. You're expecting to see this answer of 0 over 0, okay? So in the beginning of our course, when we first started doing these limit problems, it was kind of up to you to know your algebraic methods. And there's a lot of factoring involved. There's a lot of trigonometric identities, all of these things. Well, it's the night before the exam. I'm not going to mince words with you. We're just going to cut to the chase. Your best friend on these problems on that exam tomorrow is L'Hopital's rule. You want to go and you want to make use of L'Hopital's rule. And hopefully you've all been introduced to L'Hopital's rule. L'Hopital's rule says that if you get an indeterminate form when you do direct substitution, that you are allowed to use L'Hopital's rule, which says take the derivative of the numerator, take the derivative of the denominator, and try that limit again. So in this example, we have found that we've got an indeterminate form. Now, for those of you who need the refresher, the indeterminate forms are in 0 over 0 or infinity over infinity, and it can be plus or minus infinity. It doesn't matter if it's a positive or a negative. If you get either of those forms, that means L'Hopital's rule is in play, and by all means, just start using it. Take the derivative of the top, take the derivative of the bottom, and see what you get. So this is a multiple choice question. We don't need to be really careful about how we write it, because all we're doing is bubbling in A, B, or C. I just want to take a moment and tell you that if this were free response, what you would have to do is the following. I'm just going to do it for this first example. I'm not going to do it for all of our examples. But if this were a free response, what you would have to do is you would have to show that the numerator goes to 0, and then you would have to show that the denominator also goes to 0. And you would need to show that independently. You'd have to show it as two separate limits. This notation of 0 over 0, the AP people are not a big fan of it. It's actually kind of poor notation to say anything is really equal to 0 over 0, since that's really an undefined value. So again, in free response type questions, if this were an FRQ, you would show that. And after that, you would just launch right into L'Hopital's rule. So you could say, now using L'Hopital's rule, we're going to try this limit again. When we take this limit, we're going to take the derivative of the numerator and the derivative of the denominator separately. So the derivative of x cubed plus 8, that's a nice simple one. We're going to get 3x squared and then minus 0. And then the denominator, we're going to get 2x minus 6. And we're going to try this limit again. Okay, so now we're going to go ahead. We're going to substitute back in. When we substitute the 2 into the top, we're going to get 3 times 2 squared. That's going to be 12. And when we substitute into the bottom, we're going to get 2 times 2 minus 6. That's going to be 4 minus 6. That's going to be negative 2. This is going to give us an answer of negative 6. So that's the answer that we're going to be looking for. Now, in my hope to get through as many different topics as I can this evening during this hour, I'm not going to show a lot of the multiple choice answers, just on a couple of them. I want to focus on the skills, especially in these first set of problems, so we can go through them as quickly as possible, okay? So there's one example. That's a straightforward algebraic limit. And again, L'Hopital's rule is where you want to go. So the next example, okay? This time we've got a limit at infinity. And as you look at this, we look at this limit at infinity, what's going to end up happening in this one is the top is going to go to infinity and the bottom is also going to go to infinity. And that's because the degree on the top, we're looking at that n squared, he's going to dictate what happens. As n goes to infinity, that 3n is going to become less and less important. So this is going to dictate what happens. That's going to go to infinity. On the bottom, again, even though this is a large coefficient of 10,000, not going to play a role as we go to infinity. So the n squared on the bottom is going to play the role. So we've got that infinity over infinity. We are going to take this limit as n goes to infinity, but we're going to make use of L'Hopital's rule again. We're going to take the derivative of the top, which is going to be 8n minus 3. We're going to take the derivative of the bottom, which is 2n plus 10,000. When we look at this one, this time through, again, what we're going to find out is that the numerator is going to infinity and the denominator is going to infinity, because again, we've got these n's that are dictating. Not a problem. L'Hopital's rule can be used over and over again. As long as you have an indeterminate form, you are allowed to continue to use L'Hopital's rule. So this is a double L'Hopital's. We're going to do it again. And this time, we're going to take the derivative of 8n minus 3. That's going to give us 8 on the top. And on the bottom, we're going to take the derivative of that 2n plus 10,000. That's going to give us a 2 on the bottom. And what we're going to end up with is an answer of 4. So that is our final answer on this one. So L'Hopital's rule can be used repeatedly. That's something I wanted to stress. The next one, this is a problem that we never saw all that often about 10, 15, 20 years ago, but it's been showing up quite a bit. And the idea here is, again, we're going to do some substitution. We're going to try to think about what's going on. Clearly, the top is going to go to infinity, and the bottom is going to go to infinity. Again, L'Hopital's rule all over this. So when we go to do the limit, and we're looking at the numerator, we're going to get 100x to the 99. And when we do the denominator, we got e to the x. Derivative e to the x stays e to the x. So we're going to get infinity over infinity again. Well, we just got done saying that you could use repeated application of L'Hopital's rule as long as you continue to get an indeterminate form, which we have. So we're going to take L'Hopital's rule again. But this time we're going to end up with 9900 x to the 98th. And the bottom is just going to stay e to the x. So at this point in time, we're going to get infinity over infinity again if we do direct substitution. But here's what you need to think about. Okay, you use your noodle here. We're going to keep getting infinity over infinity because every time I take the derivative, I'm just going to take this down by 1. I'm always going to take that exponent down by 1. But the bottom is e to the x, and e to the x is never going to change when we take its derivative. It's always going to stay the same. So somewhere down the road, we're going to keep doing this over and over and over again. And what's going to end up happening is I'm going to get the limit as x goes to infinity, and I'm going to have some god-awful constant out here. It's going to keep getting larger and larger and larger. But the x exponent is going to keep dropping down, 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 down. Eventually, it's going to get down to x to the first, and we're going to have an e to the x on the bottom. That's still infinity over infinity, but this is the end of the line because now the next time I do L'Hopital's rule, I'm going to have that constant on the top, and it's going to be e to the x on the bottom. Now this constant is going to be 100 times 99 times 98, all the way down times 3 times 2 times 1. It's going to be a large number, but it's not going to be as large as e to the x, okay, when x goes to infinity. So you're finally going to wear down the numerator. And what's going to happen is the denominator is going to go to infinity. The numerator is going to be a constant. That means we're going to end up at 0. So what I want to point out about this one is sometimes you got to think about patterns. You got to think about what's going to happen if we keep doing a repeated application, because there's no way any of us have time to take these 100 versions of L'Hopital's rule. But we can tell this. If we have a polynomial, any polynomial at all, over any exponential function in that limit, if we keep getting an indeterminate form, when we take the derivative, the polynomial will eventually go away if we take the derivative enough times, and the exponential function will always stay in the bottom. So as long as we have this relationship, we can kind of cut to the chase. We're going to get down to the end where the numerator is going to end up being a constant and the denominator is going to end up being an exponential function. We're going to end up with 0. So that is some of the more straightforward type limit questions that we're asked. Now, I want to make sure you guys are good with your tools. So in the next 3 questions, we're going to be looking at derivatives. So in each of these problems, we're going to be taking derivatives. I went through and I looked at the last 5, 6, 7, 8 years worth of exams, and I looked at the type of problems they had on those exams, and I wrote problems of similar difficulty, and that's what I'm sharing with you tonight. So all of these questions are not the exact questions that are in the exam, but they're the same type of question, same level of difficulty. So when we look at this one, you've got to think about how you want to take this derivative. Hopefully what you're going to see right away is this is a product rule, okay? So we're going to take the derivative of both sides of this equation. The derivative of y is dy over dx, so we're going to write that there. And now we're going to focus on this x squared times 3x minus 10 raised to the 2/3. There's all sorts of ways you can remember the product rule. A lot of you guys probably think about the derivative of the first times the first times the second plus the derivative of the second times the first. What I have done in doing product rules is I've found a way to kind of organize that idea by just making these boxes, making compartments. Because what I'm going to do now is I'm just going to focus on one factor at a time. And the derivative of x squared is 2x. And now I'm going to take the derivative of this guy. This guy is a chain rule. There's an outside function and an inside function. So we're going to use the chain rule on this. The derivative of the outside here is 2/3, and then we're going to drop that to the negative 1/3 for the outside function. We're going to copy the inside for the derivative for step 2 of the chain rule, and then we multiply by the derivative of that 3x minus 10 which in this case is 3. So for those of you who think about the derivative of the first times the second plus the derivative of the second times the first, let me show you what's going to happen. That right there, if I go in that diagonal, that is the derivative of the first times the second right there. So I'm just going to write that as part of my answer. I'm going to get 2x times 3x minus 10 to the 2/3. So there's that one. And then I like to go plus, and then I'm going to go the derivative of the second times the first. And that's going to give us that answer that we're looking for that product rule. So that's going to be plus x squared times, and let me just give myself some space here. We're going to have times, well, I'm going to do a little simplifying on the way here. 3 and that 1/3 are going to cancel. We're going to be left with a 2 in the top, and then that 3x minus 10 raised to the 1/3 is going to be on the bottom because of the negative exponent. So this is going to be our answer right here. This is what we're looking for. This is the answer that you're probably looking for in that multiple choice. Okay. So again, just some quick skills, making sure everybody's up to par with their derivative skills. For this one right here, I'm just going to give you a second. I'd like you to work this out on your own. I'm going to give you about a minute and a half, and then I'm going to come back and do the work and check with you guys. Okay. In this particular example, the key to this is making sure that you're not wasting your time doing the quotient rule over and over again. Use your laws of exponents. Rewrite this expression. An x cubed on the bottom is an x to the negative 3 when you bring it up. An x squared on the bottom is an x to the negative 2 when you bring it up. So what we're going to have is a bunch of terms that we can actually go term by term and take this. So again, we're going to go term by term, starting with derivative f of x, that's f prime of x. Then we're going to get 4x cubed. On this next one, we got to be careful. We're going to do negative 3, but it's going to be times that coefficient of 2, so it's going to be negative 6x to the negative 4. This next one is going to be positive 6x to the negative 3. And then the derivative, of course, of 4 is 0. So we're going to end up with this. Please, 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 just take your time. Be careful when you're subtracting. I've seen so many students do negative 3 minus 1 and get negative 2, okay? Make sure you're focused, you're taking your time. Don't rush, okay? If you take an extra 5 seconds to make sure you get it right, it is well worth it. 5 seconds for a correct multiple choice answer is an easy trade-off on this exam. So again, be focused, be deliberate, take your time, make sure you're doing everything right. The key here is to make sure that everything you know how to do, you get right. Okay, so what I'm going to do now is I'm going to go through and I'm just going to remove all the negative exponents, which means I'm going to drop these back to the denominator. So that's going to be minus 6 over x to the 4th. And then the 6 stays in the numerator, but the x cubed is going to go to the denominator. And this is going to be our f prime of x. So in this example, we were asked to find f prime of 1. F prime of 1 is going to be when we substitute 1 in for all of our x's. So I'm just going to make a template here so I can do that easily. So in goes 1 for each of them, and we're going to end up with 4 minus 6 plus 6, and that's just going to give us the answer of 4. Okay, so there you go. And on this one, again, please, please, please be very careful. They also love doing problems like this, but throwing a negative one in there. Again, super careful with the negatives because you're going to have signs changing on these odd exponents, so just be really, really careful. This one was a little more straightforward because we had a positive one. All right. So both these types of problems you're going to see on the multiple choice. Here is what is considered to be the kind of the most complicated looking one of the multiple choice derivatives, okay? Because now you're taking a derivative, but you're actually taking a derivative integral. So the way this one's going to work and the way that you want to set this up is basically, I always tell my students, we don't differentiate integrals. We don't. We never take the derivative integral. Instead, what we make use of is our friend called the fundamental theorem of calculus. So what I'm going to do is I'm going to give this guy a name because the fundamental theorem is all about giving your functions good names. I'm going to call this little g of t. So when I do this, here's what's going to happen. I'm going to have capital F of x is equal to this integral from 0 to 2x. But now I'm going to have my square root of t squared plus 9 dt. But instead of integrating that by hand, I'm just going to integrate it using notation. So I hope you guys are familiar with the parent function idea. The parent function of a little g of t is going to be a big G of t. So this is going to be big G of something minus big G of something, because I'm using the fundamental theory of calculus. Now, I'm going to evaluate this at our top bound of 2x. I'm going to evaluate our bottom bound of 0. So far, I really haven't done anything. All I've done is just rewrite capital F of x. And the reason I want to do that is because now I got some choices. I'd like to take the derivative of this, but that's the same as taking the derivative of the integral. But now here's where it pays off. It's really the same as taking the derivative of the fundamental theorem of calculus. So when I look over at that fundamental theorem, here's what you have to remember. We don't take derivatives of integrals, we take derivatives of fundamental theorems. So here's where we're going to get the answer. We're going to go and we're going to take the derivative of capital F of x, which is capital F prime. I'm going to bypass this middle, and I'm going to go straight to the fundamental theorem. So here is where I'm going to get the answer for the fundamental theorem, okay? So this is, if you're not sure, always do the chain rule. I can't stress that enough. The chain rule is always kind of a safe bet. So a lot of people are going to look at this and incorrectly say that the derivative of big G is little g, so this is going to be g of 2x. Not going to work. You got to do the chain rule. The derivative of big G of the outside function, the big G of something, is little g of something. Now we're going to copy that inside function, 2x. Now the chain rule says you have to take the derivative of that inside function. You're going to have an extra factor of 2 there. So make sure you do the chain rule. If you don't, you'll lose that factor. Here's another really common mistake. Okay, people are going to go and they're going to take the derivative of big G of 0. They're going to say it's little g of 0. Well, again, if you do the chain rule on this, which is it's a little bit of overkill, I'll admit it. But if you do the chain rule on this, it's going to be little g of something. Copy the inside, you're going to get 0. And now you've got to take the derivative of that inside. All of this is going to get multiplied by 0. In other words, the derivative of that term is 0. So computationally, that's how you would see it. How would you know it? Just by using a little bit of common sense. There's no variable here. You've replaced the variable with 0. This is a constant. The derivative of any constant is 0. Okay? So now what do we know? We know the derivative of big F prime, and it's equal to 2g of 2x. Well, we're ready to go. We now want to find big F prime of 2. That means we're going to substitute in a 2. So it's going to be 2g of 2 times 2x. I'm sorry, 2 times 2, because x is 2. That's going to give us 2g of 4. Now, at this point in time, a lot of my students, they get a little confused because we've been so long. They're like, well, wait a minute, how do I figure that out? Well, this is where good labeling comes in. Okay, I'm just going to slide this down. What I mean by good labeling is right here, we said that g of t is this guy. So we're going to make use of that. That tells us this is now 2 times g of 4. Well, if g of t equals the square root of t squared plus 9, then g of 4 is going to equal the square root of my input squared plus 9, and we're plugging in 4. So we're going to get 2 times the root of 16 plus 9. That's 2 root 25. That's going to give us 10. Okay, so I've chosen this problem for a couple of reasons. One, it does show up on the AP exam very, very often. Another way you'll see it is you'll see it written like this. You'll see take the derivative of an integral. You'll see it written like this a lot of times. Okay, it might be x here, it might be 2x, and then you'll have some function, whatever the function is here. This is the same idea. Okay, this is the same idea. You've got to use the fundamental theorem to give it a name so you can go notational and then go back. The other reason I like choosing this problem is I can pretty much guarantee you'll be on the free response somewhere. The fundamental theorem over the last 10 years has been the most tested topic in calculus, in my opinion. So I want to throw as much fundamental theorem at you tonight. Megan and I are both doing some problems on fundamental theorem. I know she just did that one with the triangle right before I signed on. So you're going to see it a lot tonight because you're going to see it a lot tomorrow. Okay, so those are our derivative problems. Now, some of you guys I saw before I got on were asking for U-Substitution. So we're going to talk about some integrals real quick here, okay? So these are the 3 integrals we're going to look at. This is the first of the 3. You've got to know your integrals. You got to know them pretty well. And if you do, one thing that you know is that you're supposed to be familiar with the integral of e to the u, okay? E to the u du. That's one of the integrals you're supposed to know. The other thing you're supposed to be familiar with is the property of integrals that says constants don't matter, because you can just pull them outside the integral. So we're going to rewrite this. We're going to rewrite this as 8 times the integral of e to the 3x dx. Now, for those of you guys who were with me in the stream when we did unit 6, we talked about U-substitution in that stream, okay? So if you have some time, you want to go back and look at more in-depth integration problems, go back and look at the unit 6 cram. You're going to see this all done out. I'm going to do this fairly quickly. Here's the idea. I know how to integrate e to the u. The integral of e to the u is e to the u plus c. I've got e to the 3x. That tells me pretty straightforward that if I let u equal 3x, these guys are going to be a good match because I'm going to get e to the u, okay? But here's the one thing you got to remember. You got to go piece by piece. You got to account for everything, okay? So I like to call, when I do these integrals all the time, I'm just going to do it this way because I'm going to slip and I'm going to say if I'm not thinking about it. I like to say there's an x world where we write all the x's, and there's a u world where we keep track of how that looks when we replace everything by u's. And the two things you got to remember, okay, is that if you are a function or a constant, you're allowed to go in both places. So functions can cross over and constants can cross over. So what I'm going to do is I'm just going to do a whole bunch of bookkeeping here. The first thing I'm going to do is take care of that integral sign. And that is a function, so the integral sign can walk right in. The next thing I'm going to do is I'm going to take care of this e, because e is a function, so it can walk right in. That's e raised to the something. I'm not sure what it is, but it's e to the something. Now, the next thing I want to do is this. The next thing I want to do is I want to take care of that 3x. But x's are not allowed to go into that u world. So if you have an x in it, you got to enter what I'm calling this box where I'm kind of organizing my idea. So I enter the box as 3x, but I'm saying my substitution that u is the same as 3x, so I'm going to leave the box as u. Now, here is the trick. How do you handle the dx? You can't just write du over here. That's not right. You know, dx and du aren't necessarily the same thing. So what do you have to do? You have to find a way to encode that differential. And the way you're going to do it is you're going to take the derivative of this equation right here. So every time you choose your u, the next step you should do is take the derivative of that u. So when I take the derivative of this u, I get du with respect to x. So it's du over dx equals, and then it's 3. And now, because I want to separate the u's from the x's, I'm going to write du equals, I'm going to multiply both sides by dx, and we'll write 3dx. This is so important. This is how you're going to handle the differential every single time. So you bring the differential into the box, and what you're saying is, what does dx equal? Tell me what dx equals, because that's what I'm going to bring over into u world. So you look in the box, and what you see is you've got an equation with dx here. So your job is to solve that equation for dx. That's what you want to do. So you're going to solve this equation for dx. In other words, you're going to isolate this guy right here. You're going to multiply both sides by 1/3. And you get 1/3 du equals dx, okay? So when you go to bring over this dx, it enters the box as dx, but it's going to leave the box as 1/3 du. So I'm going to get du over here, and the 1/3 is a constant. It's going to stay out in front. What happens now is everything is accounted for. I've accounted for everything. If you want to account for the constant out front, you can. I'm going to leave it here because we're just going to come back, so it's going to be waiting for me. As a matter of fact, I'm going to go ahead and I'm just going to write this down here to remind me that the answer is going to be multiplied by 8. If you wanted to bring it over, you know, you can just bring it over. It's a constant. It doesn't make any difference as long as you account for it the right way. So now you're in U world and you're looking to integrate a new integral called e to the u du. That's one step. And then when I say a one step, I mean one you know just from doing it so often. Okay, we call one steps in my class. So the integral of e to the u is e to the u. We've got an 8/3 out in front. So there is our answer in U world. But now the idea is to bring it back. You got to bring it back, and you're going to follow the same rules. Functions can go anywhere. Constants can go anywhere. U's have to go in the box and be coded as x's. So what's going to happen is I'm going to bring that 8/3 over. Now remember, I already had the 8 over there, so it's just going to be the thirds that's going to come. That e is going to come back as a function. That's going to be e to the something. And now I've got to take this u back over. Remember, u has to go through the box. It enters the box as u, and it leaves the box as 3x. So we've got this. We've got 8/3 e to the 3x. And now the last thing, the cherry on top of every integral, of course, is the plus c. Don't forget that plus c, okay? So you're going to have 8/3 e to the 3x plus c. All right, that is an opening example for U-substitution. We're going to look at 2 more examples because I know people are asking for it. So without any further ado, let's scroll down. And on this one, what I'd like to do is give you guys about 45 seconds. Probably not enough time to finish, but enough time to get started. So go ahead, take 45 seconds and see if you can set the integral for this one. One of the big questions my students ask me every year is, how do we find the U? How do we know what U is? So, normally I would make my kids go home and practice hundreds and hundreds of integral problems, but seeing as the exam is tomorrow, I'm going to cut you guys some slack. Here's how you pick the U. The U is always the inside function. It's always going to be the inside function. That's what you're looking for the U. You want to choose the U so it's the inside function. So when I look at this, the inside function here is 4 minus x squared. I'm always going to choose U, then I'm always going to take its derivative. So the derivative of 4 minus x squared, the 4 is a constant, derivative is 0. The derivative of negative x squared is negative 2x. And there is my derivative. Now, what you're going to see is you're going to get this every time, but then you're always going to multiply that dx over to that side every time. So I'm just going to jump right down to this expression right here. I've got u equals 4 minus x squared. I've got my du equals negative 2x dx. This is this forms the components for the box, as I call it. And now we're going to try to bring everybody over into U world through this box, okay? So again, using the bookkeeping, making sure I don't leave any parts out because that's one of the most common mistakes. I'm going to start with the integral sign every single time. So in comes the integral. I am then going to do the square root on this one. That's a function. And I'm going to bring it over as something to the 1/2 power because I know that's the way I like it to look so I can integrate it. Now what I'm going to do is I'm going to tackle that 4 minus x squared. Because there's an x involved, I got to bring that through the box. It's going to enter as 4 minus x squared. It's going to leave as u. So I think everyone can see that, this is clearly the square root of u based on our substitution. That's what we've got. But now I've got some pieces left over, right? I've got this x and I've got this dx. So one of the most important questions to ask now is, do you want to bring this together or do you want to bring them separately? Okay, what do you want to do? Well, you don't have to worry about making that decision, okay? That decision is made for you. Oops, that decision is made when you look in the box and you see what is in there. Let me explain. Remember last example? We were asking what is dx equal? That's what we were doing here. We were asking what is dx equal? Well, in this example, my leftover pieces are x dx. So I want to go to the box and I just want to say, hey, box, is there a way I can solve for x dx? Is there any way you can give me an equation that has an x dx in it and I can solve for it? And lo and behold, what do I have? I've got x dx right there. So I'm going to isolate that x dx. I'm going to solve for it, which means I am going to multiply both sides by negative 1/2. Okay, divide both sides by negative 2. Same idea. So when I do that, I'll get a negative 1/2 on the left side. I've got my du, and I have been able to figure out what x dx is. So these two guys right here, x and dx, are going to enter the box together as x dx, and they're going to come out the other side as negative 1/2 du. Negative 1/2 goes out in front, du at the end. We've got a brand new integral. That's the whole idea behind U-Substitution. Write it as a new integral. It has the same value. It just looks a little different, and maybe we'll be able to integrate it easier. This one right here, I always call this integral the integral of u to the n. It's one of the most famous integrals out there. So the negative 1/2 gets a free ride, goes right to the answer. And then I'm going to do u to the 1/2 plus 1 over 1/2 plus 1. All right, and again, I'm just doing this out, making sure I don't make any careless errors. It's really easy to be careless on this, but that's what it says. So now I'm going to end up with negative 1/2. That's going to be u raised to the 3/2. It's going to be over 3/2, but when you divide by the 3/2, you're really multiplying by the 2/3. What's going to happen now are those common factors are going to cancel. I'm going to get negative 1/3 u to the 3/2. And now it's time to bring this back into x world. So the negative 1/3 is going to come over. The something to the 3/2 is going to come over. That's a function. All right, so the negative 1/3, the something to the 3/2. The only thing left is the u. The u has to go in through the box. It enters the box as u. It leaves as 4 minus x squared. I get 4 minus x squared there. And then remember, like I said before, the cherry on top is that plus c. Do not forget that plus c. Some of you guys will be sticking around for the entire evening. We're going to be doing some separable differential equations when I come back in the second section. And that plus c is going to play a huge part of that, okay? So there we go. That's the integral on that one. So for this next one, we're just going to do this one really very quickly because I'm looking at my time. We got a lot to cover this evening. This is another U-substitution. So again, it's going to be u equals, it's going to be du over dx equals. A lot of people wonder, where's the inside function on this one? Well, this is one that you want to match this to 1 over u du. So the inside function is actually the denominator. So we want to use 2 minus 5x. Okay, we want to use 2 minus 5x. The derivative of that will be negative 5x. I'm sorry, my mistake. Negative 5, negative 5, just negative 5. And then we're going to multiply both sides by that dx again. So we're going to end up with that. Okay, negative 5 dx. Here we go. We're going to bring it over. We're going to integrate. So integral comes over. Let's do my bookkeeping. Make sure I don't lose anything. The fraction bar is going to come over. 2 is going to come over. That's a constant. It's going to go out in front. The 2 minus 5x is going to come over through the box. It's going to enter as 2 minus 5x. It's going to leave as u. And then the only thing I have left now is the dx. Well, I go into the box again. I find the dx, and sure enough, there it is. So I isolate that dx, and I get that dx is equal to negative 1/5 du. So we're going to bring the dx in. It's going to come in as negative 1/5 du. That's going to put sorry, let me change my marker. It's going to give me a negative 1/5 out in front. It's going to give me a du at the end. And now the placeholder in the numerator is that 1. Okay. So now what's going to happen with the bounds? And you've got a choice here. You can do it either way. You can choose to bring your bounds to U world and finish this problem in U world, or you can integrate this in U world and send it back to X world and then do the bounds when you go back. I'm going to show you bringing the bounds into U world today. Here's what I'm going to do. I'm going to bring those bounds right in. And I'm going to say that, okay, if this was x equals 3 and this was x equals 5, over here it's going to be u equals in both cases because I'm in U world. So what I've got to do is I'm going to ask, when x equals 3, what would u equal? Well, that's where this comes in, okay? So if x equals 3, I'm going to get that u is equal to 2 minus 5 times 3. That's 2 minus 15. That's going to be negative 13. So we're going to put negative 13 there. Okay, we're going to put negative 13 there. All right. So now what's going to happen? We're now going to go and we're going to bring in the x equals 5. But now if x equals 5, that means that u is going to equal 2 minus 5 times 5. And that's going to give us that u is equal to 2 minus 25. That's going to equal negative 23. Okay, so that's going to be our u bound, negative 23 up there. So now what we're going to do is we're going to integrate this. This is going to be the natural log of the absolute value of u times negative 2/5. And from here, you're going to evaluate that u equals negative 13 and u equals negative 23. All right, I'm just looking at our time. I'm going to end up just kind of leaving this one for you guys to finish on your, well, just real quickly, I guess, not that big of a deal. We're going to integrate this. It's going to be the ln. And we're going to evaluate it at both bounds. I guess I can finish this. It's going to be negative 23 in there, negative 13 in there. That's going to be negative 2/5, the ln of 23 minus the ln of 13. And one last thing, it has been shown on the multiple choice exam a couple of times over the last years that they like to use logarithm rules. When you subtract logarithms, it's the same as dividing the inputs. So you can actually take ln of 23 minus ln of 13 and make it the ln of 23 over 13. And then that would be your final answer on this one. Okay, so these first 9 problems we've done, these are the skills. If you're very, very comfortable with each of these problems, you're going to be very ready for the first 15 or so problems tomorrow. Okay, so let's go back to.
All right, so let's get back to integration by substitution. Let's take a look at this example. This is a really common question we've been seeing on the AP exam over the last several years. They give you an integral and they actually provide you with the substitution they want you to make. So here in this problem, they're asking you which of the following integrals is equal to our integral from 0 to 4 of x times root x squared plus 9 dx if you make the substitution u equals x squared plus 9. Okay, so in this example, we know we've got a U-substitution. We're not even being asked to integrate it. We're just being asked to bring this kind of into what I call U world, where everything is being written in terms of U, and find out which of these four integrals matches to our integral. So let's take a look at this on the tablet. So the idea here is just to go in and do your typical U substitution problem. So we're going to start this problem and we're going to say, okay, we're going to do the U they asked us to do. So I'm going to just copy this integral over. We're going to do the integral from 0 to 4 of x times the square root of x squared plus 9. Now, one thing I always do in my classes is I always stress the idea that the bounds have variables associated with them. This is really x equals 0. And this is really x equals 4. Now, most of the time that doesn't matter because it's just obvious we're dealing with a differential of dx, so we know that. But I like to just point that out, especially in a problem like this, because now we're going to do a substitution where u is equal to x squared plus 9. We're going to find that our du is going to be equal to 2x dx. So for all of you guys out there who wanted some review and U substitution, here we go. The idea is to bring our integral from what I call x world, where we do everything in terms of x, and we're going to bring it over here where everything's done in terms of u. So I refer to that as u world. So the way that works is you're allowed to bring over any function and any constant you want. So I'm going to start by bringing over the integral sign, because the integral sign is a function, so that can come over. And then I'm going to bring over the square root next, okay, because that's a function. So we can bring that over, and we're going to bring that over as the square root, and we're just going to leave it open because right now what we've got to do is figure out how to bring over the rest. Everything else has an x in it. So now I've got to figure out how to bring over this x squared plus 9. So what I like to do is I like to kind of really emphasize this is my substitution box. This is how things are going to get changed from x to u's. So I'm going to bring this x squared plus 9 over to the box and be like, how do I encode that using u's? And they told us they wanted us to use that u was going to be equal to x squared plus 9. So u is going to go over here. So he's all checked off. At this point in time, the only two things I've got left are x and dx. So the question is, how do I handle this x and this dx? Well, they're both x's, so they got to go through our box. So the question that normally happens here is, do you want to bring them over together as one group, or do you want to do them separately? The good news is you don't need to answer that. You're going to go look at your box or your substitution, and you're going to go to that box and you'll be like, I need to find an x dx. If you can find an x dx in here, it's going to tell you how to bring them over together. So I come in here and I'm looking for x dx, and sure enough, there's x dx right there. So I'm going to isolate x dx. In other words, I'm going to solve this equation for x dx by getting rid of a multiplication by 2. I'm going to multiply both sides by 1/2. That means that when x dx comes into the box, it's going to enter as x dx, but it's going to leave as 1/2 du. And I'm going to put that 1/2 out in front, and I'm going to put that du at the end. Okay, so now we can look at our answers and we can start to see that we're starting to get an idea of what our final answer is going to be. And we see some similarities, especially with B and with D. We've got that 1/2 on the outside. I'm pretty confident about that. I've got the square root of u du in both of these. So the only question now is, what are we going to do about the bounds? Well, for those of you guys who just leave 0 to 4 there, you might think, well, 0 and 4 don't have an x in it, so I can just bring it over. But then you would fall for the trap and pick B, because that is an x value. It's x equals 0. It's x equals 4. So you've got to bring that through the box as well. So you've got to take x equals 0 over here to the box and say, hey, what happens when x equals 0? And in this case, what happens when x equals 4? Well, the place we're going to do that is the substitution that they gave us. What does u equal? So we were told that u is equal to x squared plus 9. So if x equals 4 and u equals x squared plus 9, well, that means that u is going to equal 4 squared plus 9. That's going to get us 16 plus 9 is 25. And that means our x equals 4 turns into u equals 25. This is going to be a top bound of u equals 25. We're going to have to do the exact same thing with this x equals 0. We're going to want to bring that into the box again. We're going to go to that u substitution they gave us. So now if x equals 0 and u equals x squared plus 9, well, that tells us that u is going to equal 0 squared plus 9. And we're going to get that u is equal to 9 for the bottom bound. So now we know the bottom bound is u equals 9. This is what you have to remember. The bounds have to be substituted for as well. So you want to bring the bounds over just as much as you want to bring over the integrand and the differential. We now know that we're looking for a 1/2 root u du. We also know that the bounds have to be a bottom bound of 9 and a top bound of 25. We are going with answer C on this all the way. Okay, answer C is the answer we're looking for. Oh, I'm sorry, my mistake. I almost made a mistake. Answer D, my mistake. Again, it's a 1/2 out in front, not a 2. It's very easy to make that mistake. So you guys be careful when you're taking that exam tomorrow, okay? So it's 1/2 out front with a lower bound of 9 and an upper bound of 25. And of course, the square root of u du is what we're going to integrate. Very common question. Remember to bring your bounds over, okay? So the next example I want to look at with you guys, again, another common question on the AP exam. It's using properties of integrals. So this is a really common type thing where they give you a bunch of information about a bunch of different integrals, and you've got to figure out how to piece that all together to get information about a new integral. So what I encourage you to do is I encourage you to look at what you're trying to get. Okay, go straight to that. We're trying to get 1/2 the integral of 1 to 5 of g of x minus f of x. The given information, what I'm seeing is I've got some integrals from 1 to 12, and I've got an integral from 5 to 12. So first thing I want to do is I want to get an integral with g of x minus f of x in the same integral. That means they have to have the same bounds. I'm going to put these two integrals together and find out what kind of information I can get from that. So using those two integrals, what I'm going to do is I'm going to integrate from 1 to 12. And what I want to do is I want to start with this one because we've got that constant of 3 down there. Now, you guys know that that constant of 3 can be rewritten in the front as a 1/3, okay? And then once you know that, what's nice about this one is the integral from 1 to 12 of g of x dx. Well, with the 1/3 out here, it's equal to 5. But if you multiply both sides by 3, you're going to lose that 1/3. And when you lose that 1/3, this is actually going to turn to a 15. So now we know what g of x is doing from 1 to 12. We know what f of x is doing from 1 to 12. This is how we're going to be able to combine to get information about these two functions together. So I'm looking at where I want to go, and I want to get g of x minus f of x. So I'm going to set it up that way. So I'm going to go from 1 to 12, and I'm going to do g of x minus f of x as my integrand. And we know what that equals because we know that from 1 to 12, g of x is 15, and we know from 1 to 12, f of x is 14. So this is really just going to give us the answer 15 minus 14, which is equal to -1. So what we've got now is we've got this entire integral from 1 to 12. Now remember, they're asking us about 1 to 5. So we're just looking for part of this integral. But here's where the other piece of the information comes in. We know what's happening from 5 to 12. We know from 5 to 12 what's going on here. So what I want to do again is I want to rearrange this so the integrands match. All right, my integrand is the reverse of what I really want here. So using properties of integrals, I can rewrite this integral from 5 to 12, and I can change the direction of the integrand. I can make it f of x. Instead of f of x minus g of x, I can do g of x minus f of x. Now, remember, what that's going to do is it's going to basically put a -1 factor out in front. All I've done is I've factored out -1. It's still equal to -7. But now the good news is when I multiply both sides by -1, I now know this integrand from 5 to 12 is equal to 7. So putting these two pieces of information together, putting this one together with this one is going to be what we need to do. Because the integral from 1 to 12 of g of x minus f of x dx can be broken into two smaller integrals. It can be broken into starting at 1 and going to 5 of g of x minus f of x dx. We're keeping the exact same integrand. And now we can break that up from 1 to 5, and then we can continue by starting again from 5 and going to 12. And that's of g of x minus f of x dx. As long as we keep the integrand the same, we're all set. So now what have we computed already? Well, we know that this first integral, based on our work right here, is -1. We know that this second integral is kind of what we're after. That almost is a perfect match for what we're looking for. Yeah, there's a 1/2 there, but it's the exact same integral. So if we can find the integral, we can multiply that by 1/2 in a minute. So we're just going to keep this integral exactly the way it is, because that's actually what we're trying to find. And now we know that this integral, based on our previous work, is equal to +7. Okay, that's equal to +7. So from here, what are we going to do? We are now going to subtract 7 from both sides, and we're going to get this is equal to -8, and that's equal to the integral from 1 to 5 of g of x minus f of x dx. Well, now we go back to what we're after. What we want is half that amount. We're looking for half that amount because we've got the full integral from 1 to 5 here. This is telling us we want half of that. So all we have to do is go back here and multiply both sides by 1/2. And we multiply both sides by 1/2. What we end up finding is that this integral is actually equal to -4. Properties of integrals, very important problem. You're going to see that a lot in the AP exam.
The next one we're talking about is the average value of a function. And the average value of a function works like this. Find the average velocity of a particle that moves along the x-axis during the interval from 1 to 5 if the velocity is given by this function. Okay? In order to do this question, what you need to do is you need to know your average value formula. And your average value formula is given by the following. It's 1 over b minus a times the integral from a to b of f of x dx. Okay, this is the average value of a function. So if we know that, we should be able to handle the average value of the velocity using this formula. So let's take a look, okay? So find the average value, and I hope my screen is working. I hope you guys are with me. So we want to do the average value. It's 1 over b minus a. Well, b in this case is 5, and a in this case is 1. So we want to do the integral of, we want to do 1 over 5 minus 1 times the integral from 1 to 5 of 3t squared minus 4t. If I work this out, this will be the average value. You're going to see a lot of problems where they just put a constant 1 over in the front of an integral. Every time they do that, check to see if it's the difference between the bounds. If it is, what they're doing is setting you up with an average value problem, okay? So if you've got a constant, like for instance, this problem had started as 1 over 4 times the integral of 1 to 5, 3t squared minus 4t dt. That's a tip-off that this is some kind of average problem because the constant out front, the 4 on the bottom, is the difference of the bounds. So when we go to integrate this, we're going to get 1 over 4, and these are pretty straightforward integrals. We're going to get 1 over 4 times t cubed minus 2t squared, and we're going to evaluate this from t equals 1 to t equals 5. So what we're going to end up with is, I always like to bring my 1/4 all the way out, and that way I don't have to worry about it. So now I'm just going to be really careful. And again, I really suggest that you guys use a lot of parentheses. Take your time. Make sure you're evaluating these integrals correctly. Okay, now I'm just putting 5 in for both my bounds at the beginning and 1 in for both my bounds at the end. So I'm going to end up with 1/4 times. Well, we're going to get 5 cubed is 125. We're going to get 5 squared times 2. That's going to be minus 50. On the other side, we're going to get 1 cubed, which is 1. And then we're going to get 2 times 1 squared, which is minus 2. Right. So again, just making sure you're careful and not making any careless mistakes with this. That's going to get us 75 minus a -1, which is going to equal 1/4 times 76. And that's going to equal 19. So 19 would be the average value there, okay? But again, just keeping in mind the average value formula. The last couple of things I want to go through with you guys before Megan comes back in and takes you guys through some free response. This is actually a good crossover because these problems I want to show you now, these are often on the free response, but they're often on the multiple choice as well. They're called interpret the meaning problems, okay? So in this one, the temperature of pizza coming out of the oven is modeled by a differentiable function C of t, where t is measured in minutes and C of t is measured in degrees Fahrenheit. Using the correct units, explain the meaning of C prime of 5 equals -3.625 in the context of the problem. What I want to do with you guys this evening is I want to give you a template. I want to show you how this is going to work. Anytime you have to interpret a derivative, okay, this is how it's going to work. You're going to set up the same way. Here's how the template looks, okay? And the way it's going to work is the subject of the story. Now, our story was about the temperature of a pizza. That's what our subject is, okay? So that subject, because we're taking a derivative, it's changing. So what you want to answer is how is it changing? So you're going to say that the subject of our story is either increasing or decreasing. And then again, because it's a derivative, you're going to say at a rate of, and what you're going to do is you're going to take the derivative, you're going to evaluate at the point they gave you, and then you're always going to use the absolute value of that. And I'm going to explain that as we go through the answer for this one, okay? Next up, you're going to want to have your units. If you leave the units out, you're going to lose the value. You got to make sure that the units are the key to this. And then at t equals whatever the bound is they gave you, and always put a unit on that. So if you use this template, you will interpret the meaning of the derivative correctly every single time. So as we go through and we think about the problem we just had about the pizza that was cooling down, what we're going to find out is that the subject, again, was the temperature of our pizza. And what is it doing? It was decreasing. We knew that because it was a negative value. So because the derivative was negative, we're going to fill in decreasing here. And the number that we found was 3.625. So it was decreasing at a rate of 3.625. And now you need those units. Degrees Fahrenheit per minute is how those units were being measured. And it's happening when t was equal to 5 minutes. So this is what you need to interpret the meaning of the derivative every single time. Some people are going to ask me this. They're going to say, can I write the temperature of the pizza is changing at a rate of negative 3.652 degrees Fahrenheit per minute? Although that's true, it is changing at a rate that is negative. You're not interpreting it enough. They're looking for you to interpret that negative means it's decreasing, that the temperature is decreasing. You always want to either use increasing or decreasing in this blank right here, okay? And that's what's going to happen. It's increasing or decreasing at a rate of 3.625 degrees Fahrenheit per minute at time equals when t is 5 minutes. All right, we're just going to do this next one real quick, and then Megan's going to be back. What happens if they ask you to interpret the meaning, but this time you've got an integral? So this one, we got a rate at which students are joining the 5 AP Calculus cram session is modeled by our differentiable function W of t. This case, W is measured in people per hour, and t is measured in hours after the start of the session. Selected values of W of t are given in the table below. We're being asked to approximate the integral from 1 to 3 of W of t using a right Riemann sum and explain the meaning. All I'm going to do right now is just look at explain the meaning. These, as you're going to see in some of the free response questions Megan and I do later, these go hand in hand with Riemann sums. But again, what you want to look at is that W of t is being measured in people per hour and t is being measured in hours. So what's going to happen in this one? Well, here is the template that we need to interpret the meaning of the integral. Looks very similar. But again, you're going to want to know the subject. Now, the subject for us in this case was the students joining our stream, okay? You're going to want to know whether or not it's going up or it's going down. You're going to have the value of your integral and the units, and then you're going to say over the integral from t equals your first bound to t equals your second bound. So here is that template again, okay? Slightly different than the derivative one, but this is for the integral because the integral is accumulating. So what are we accumulating? Well, the subject is the number of 5 students. And it's gone up. As time has gone on, more and more of you have tuned in. Okay, so it's increased by 2,500 was the, if you did the Riemann sum, you would have gotten 2,500 as your answer for that Riemann sum. And it was being measured in students. So the number of 5 students has increased by 2,500 students from the time the first hour ended to the time when the third hour ended. So there is the template for the meaning of an integral. We are going to switch over. Megan's coming back to do some free response questions with you guys. And I will see you guys again in about 90 minutes. So Megan, if you want to take over right now, please feel free.
Let me change this back to my other webcam. All right, awesome. Hi, everyone. Thanks, Jamil. Great work, great hour there. You guys are 2 hours in, and let's keep going. Let me share my screen. We're switching gears now, going from looking at some multiple choice questions, maybe smaller, short response, to going into those big free response questions. Here we go. And so for this next hour and a half, you've got me here. So hope that's okay with you guys. I love being with you guys. So let's have a good hour and a half here. But if you're in BC Calculus, again, you won't be here this whole time because you've got about a half hour until your BC stream starts. Now, after talking to Pooja and JP, I hear that we've got a lot of questions about rate in, rate out problems. And so I'm going to actually switch this order and do a rate in and rate out problem first, because we're here for you guys and we're here to do what's best for you, and want to make sure the BC and the AB students get to see that rate in and rate out problem. Again, make sure you're stretching. 5 hours is a long time to sit. We can't see you. Do whatever you want. Get up, stretch, get a snack. Make sure you're not just starving yourself, and make sure you have water. Water is really good too for a 5 hour activity. All right. So again, just a reminder that at 7:30 Eastern time, BC will be heading over to the BC cram. So again, that's why we're going to start with that rate in, rate out problem. And we'll come back to the area and volume one for AB right after that. Again, if you are in BC and you want to see both of them, you can definitely come back and watch the stream later. It may be more helpful for you, though, in the BC stream to see the area and volume, especially if it's working with polar coordinates. We're not going to be using those here. Okay, so let's take a look at rate in and rate out in general to make sure we're comfortable with that. So it is most likely going to have a problem where a rate is increasing, but there's also some decreasing happening. So I've got some examples here for you. Here's one with a bucket with water being poured into the bucket, but there's also holes in the bucket, so water is also being poured out of the bucket, okay? And then we've got also over here, thought I'd give a nice everyday example that we can apply to real life. This is what happened in the pandemic when there was a toilet paper crisis, is what it's being called. And so here, the rate at which people were buying toilet paper was faster than the rate at which the shelves were being stocked. So this is a rate in, rate out problem as well. So rate in, rate out doesn't have to do with just liquid or anything. It can be any kind of thing that is being put somewhere and then taken away at different rates. Okay, so usually what you're going to be asked is the overall rate increasing or decreasing? And then in the case of the toilet paper, probably decreasing. And then asking also, at what time is the maximum or minimum amount? So usually we're asking about a maximum or minimum. And those of you who asked about optimization, that's about as close as we get to optimization when it comes to a problem on the AP Calculus exam. And then it probably will also ask you what is the amount at a certain time. So I've got a question for you here that we actually did a piece of in a previous stream, but we're going to do the whole thing today. And it really covers just about everything we want to see here. So that's why we're going to go over that whole thing today. So let's take a look at the first actual question, and then we'll get into going step by step through it. So this is a question from 2015. It's question 1, which means it is calculator active. And it's about rainwater flowing into a drain pipe. And it's modeled by R. And this, again, make sure you're reading closely. Let's see if I can get this to work today. The rate at which rainwater flows into the drain pipe is modeled by this. So this R itself is already a rate, okay? T is hours, we've got that. But the pipe is partially blocked, allowing the water to drain out at the other end of the pipe at a rate modeled by D of T. Okay, so rate water flows into, rate in is right here. And the rate water flows out the other end is right here, D of T. And then this, again, an important piece of information that we covered in a multiple choice question earlier. At time t equals 0, we've already got 30 cubic feet of water in the pipe. So we've got to make sure that if we ever need to talk about what's happening at 0, we've got that 30 feet added in there. Okay. So we've got 4 parts here, A, B, C, and D. First, we want to know how many flow in in the 8-hour time. And so that's just the amount of time when I was talking about. Here's the increasing or decreasing problem. What's happening at a specific time? Is it increasing or decreasing? Oh, here's our minimum. When is the amount of water at a minimum? And then we've got D, write but do not solve. And this is kind of a different part that's not always in the rate, but is always good to know because we do get a lot of these write but do not solve questions. An equation involving one or more integrals that gives the time W, and it gives you the letter that you need, W, when the pipe will begin to overflow. And we're told it can hold 50 cubic feet. All right, let's start diving into this problem. Let's look at part A. Okay, we want to know how many cubic feet of water flow into the drain pipe during the 8-hour time interval. So we don't care. Oh, sorry, I clicked the wrong thing. Here we go. We don't care right now about what's coming out. All we care about is flow into the pipe. We've got a rate here about how fast it's flowing in. And we also know that if we want how many, if we're looking for an amount and we have a rate, to me, that screams integral. We need an integral here because we want how many cubic feet. We're looking for going from a rate to a certain amount. Okay, I'm going to switch over. So we've got our R of t. T squared over 35. And then we don't need d of t right now, so I'm just going to write R of t. And we want to know how much is flowing into the pipe in 8 hours, and t is between 0 and 8. And so if we want to know how much is flowing into, we said that's an integral, and we want to know how much is flowing in 8 hours. That's just going to be the integral of R of t. Okay. Now the thing here, I told you, don't forget that when t equals 0, you see that t equals 0, we already had 30 cubic feet of water in the tank or in the drain pipe. But here, it specifically asks for how much flows in. How much flows in. So in this case, we don't care how much started. We just want to know how much fluid flows into it. So we only need this. We only need the integral here. Now, again, this is a calculator question. You do need to make sure you're letting AP Calc and the College Board and the readers know that you understand you need to take an integral and you need to take the integral of R of t. Okay. Once you write this down, you really can just use your calculator to do the rest of those steps. I use a TI 84. You can see here. I put our functions in here ahead of time just to make, this is all that we'll be using for the rest of my session with you. So if we look here, I've got R of t in as our second function here, 20 sine x squared over 35. So we're going to use y of 2 in our calculator. I'm going to show you a little trick, but you can also just type in the function if you want. So I'm going to go back to the screen. For my calculator, if I hit the math button, I go down to the 9th option. And I want from 0 to 8. And now normally in here, I'd write the function 20 sine of x squared over 35. I would use x. But because I've already saved my function in y of 2 here, instead of having to rewrite the whole thing, I can just go in here and I can put vars, go over to y vars function, and I want, oh, that was weird. Sorry, wrong button. Vars, y vars. My functions, I want to put y2 in there. That function that I have in y2, I want that to be what you take the integral of from 0 to 8. And I used x's because that's what my calculator uses in the program that I'm in. And I hit this, I get 76.570. 76.570. Again, another tip, Jamal will be going over all of them at the end, but you guys should all know this by now. You need at least 3 decimal places, okay? If you do more, that's fine. They won't even look at them. But if you do less, it is not correct. So you need 3 decimal places, okay? And so this is cubic feet of water, okay? And what is this? Make sure you understand what you've just found. Cubic feet of water, and this is what flows into the drain pipe. Over 8 hours. Okay. So I know that I can't see your chat. Hopefully you guys are asking your questions to Pooja and JP, and that was helpful for you for this first part here. let's take a look at how AP scored this. Okay, so you got 2 points here, one for writing the integral and one for the answer. So this is about the minimum you could probably write for a calculator question. If you write more around this, but this is all you have and they know this is all you need for full credit, this is what they will grade and give you a 2 out of 2. But if you are unsure how much you should write, I would always caution you to write a little bit more. If you're unsure if you need to write something, just write it down. They will look at what is correct. If they see what they need, they will give you the points for it. So you got 2 points for this piece of this one. All right. For B, we want to know, is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? And we need to give a reason this time. So we've got to make sure we know why it's doing that. So for this one, we want to know if it's increasing or decreasing at 3 hours. Well, we know that we're going to be using 3. How are we going to figure out how it's increasing or decreasing? Well, we've got the rate it's going in, and then we've got the rate it's flowing out. So if we can make something that has the relationship between these two, then we will be able to see if it's going to be increasing or decreasing. And right, if these are rates, so if it's increasing, then the rate we get as an answer is going to be positive. If it's decreasing, the rate we get is going to be negative. So what we're looking at doing is taking the amount that goes in after 3 hours, and then we're saying, well, we also have some that flowed out. So let's subtract out the amount that flowed out. If more water flowed out than flowed in, then we'll end up with a negative number, right? So if this is less than 0, then that means we are decreasing here. I should probably move over to my board before this gets too messy. If this is greater than 0, then we know we were increasing. Our rate was getting bigger. The amount of water in the pipe was getting bigger. All right, let's move over to the board and do part 2. Okay, so again, we need to find R of 3 minus D of 3, and we need to figure out what that is. Again, you have your calculator for this. So make sure you're taking advantage of what you can use your calculator for, and that this will definitely be quicker using your calculator, especially when we've got D of t. I should write D of t up here now as well, which has negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. So all you're doing is substituting in 3 for t in R, substituting in 3 for d. And what you get when you do this is, I'm not going to spend the time to go through all of that in the calculator. Make sure you're careful. Make sure you're using parentheses around what you need to use parentheses for. And again, if your function is in R of t and you're using a calculator, you're most likely just typing in x here. Just make sure you're being consistent. Okay, so R of 3 minus D of 3, we get negative 0.3136. So College Board will actually accept negative 0.313 or negative 0.314. They're okay with you truncating, and they're okay with you rounding up or down, well, not down, but rounding up when is needed. So on AP, they will allow you either of these scores to be correct. Okay, and so we got that. This number is less than 0. So that means we've got decreasing. So now, again, we can't forget that they said, give a reason for your answer. So why, how do we know? How do we know that this is a decreasing function? Well, we can say because, or since is probably a better word to start with. This is why I'm not an English teacher. Since R of 3 is less than D of 3, the amount of water in the pipe is decreasing. at 3 hours, t equals 3. Okay, and this is a complete answer here, but without this reason, this is not a complete answer. You can't just say decreasing. That is not enough. That doesn't give a reason. You need to talk about how this part that you just wrote up here makes you know that it's decreasing. So let's take another look here. Look at how AP scored this one. Okay, it's just about close to what we wrote. 1 point for just even considering R of 3 and D of 3, and 1 point for your answer. So again, make sure that you are writing down everything you think of, everything you can, and just knowing that even if you aren't sure what the final answer is, you still would have gotten 1 point out of 2 on this one for understanding that you need to think about R of 3 and D of 3 and the relationship between them. All it says is that you consider those two. All right, let's move on to part 3. All right, at what part is the amount of water in the pipe at a minimum justify your answer? Okay, so this is the part that gets a little bit more involved, I think, in the rate in, rate out, where we kind of bring in the optimization at this part. So we need to do kind of an extreme value here. We need to have a table where we're testing all of the critical points and the endpoints. Okay, we need to make sure that we've tested them all. We plug those into the function, see what we get, and go from there. So let's think about this one. What we need for this one, we definitely need R of t and D of t. Okay, so we know, let's first think about what we need for the amount of water in the pipe. So at some point, we're going to have to find the amount of water. Actually, I'm gonna wait on that for now. We don't need the amount of water yet. So I'm just going to start with thinking about what we need to know in terms of finding a minimum value. So to find a minimum, we need to test the extreme values. And we can find those by the endpoints and the critical points. So we know the endpoints already. We know that the endpoints are 0 and 8. Those are our 2 endpoints. The critical points we need to find. And we know that the critical points are when the derivative equals 0. So in general, this is just a general note. This is not to do with the problem, but it's when the derivative is 0. In our case, we need to think about the amount of water at any time is always going to have to do with this relationship between R and D. And remember, these are both already rates. So R of t minus D of t gives us the rate at which water is being either added or subtracted, depending on the time. And so this equation right here will tell us our critical points. We need a combination of the water going in and the water coming out, the rate together. That's our derivative where we need to find the critical points of. Okay, so in order to do this, we want to make sure to, I would say, use our calculator for this part. So I actually don't need any of these functions individually. I just need y2 and y3, and I need them being subtracted from each other. So I'm going to turn these off. If you guys didn't know that, you can hit the equal sign. It turns off from graphing those specific functions. So I am going to do y2 minus y3. And so this is the only graph that's going to show up because the equal sign is highlighted. And I'm going to hit graph. Actually, I don't know what my window is, so I'm just going to hit zoom 6 and then I'm going to graph it. Okay, so we've got, it looks like 3 critical points here, which makes sense. We've got 1 over here in the negatives, 1 at 0. Oh, we've got 4. Yeah, sorry, 4 makes sense. 1 over here in the negatives, 1 it looks to be about at 0. 1 right here and 1 way over here. But remember, the only part that's important to us is when x is between x, in this case t. Sorry, it's way up here. When t is between 0 and 8. So don't give yourself more work or possibly the wrong answer by not considering the correct bounds. Okay, so this one we definitely don't need because it's negative. And if we count over here, the window is 0 to 10. So this one is between 9 and 10. So we do not need this one either. Okay, so we just need the one here at 0 and the one here. Hopefully you guys know how to use the second trace and find those zeros using this button. I'm not going to cover that right now. If you need that, put that in the discussion thread. We can send you a YouTube link or talk about it there. But I'm just going to tell you what those zeros are for now. To save time, make sure we can get to this before the BC students leave for their second stream. So when you do this, these happen when t is 0. So that one we saw was specifically at 0. And then the other time it happens is when t is 3.271, about that. Okay, so now we've got our points that we know we need to test. We know what t is, and we want to know the amount of water. Okay, so we know t is 0, and 0 counts as an endpoint and a critical point. And then we also have 3.271, and we have 8. And we need to figure out the amount of water for all of those. And so now I want to go back, or forward, but back to what I almost talked about earlier. How do we know what the amount of water is? That is, like, what formula are we using for this? Well, we know that the amount of water has to do with the relationship between R of t and D of t. If we take, these are both rates, right? So if we take their integral from 0 to 8, where we subtract out however much water is being decreasing out of the bottom, that will tell us just exactly how much we need. But in this case, this specific integral that I just wrote is actually from 0 to 8 and is a specific integral that only is going to work for this one, right? So we need something that's more general. So in general, we know that the integral from 0 to the time, and now because we use t up here, we need to make sure we use a different variable to talk about these functions so that they become R of t and D of t. Okay. But are we done here? No. One thing we need to make sure we don't forget that I wrote up in the corner here for you that we talked about before. When t was 0, it was already at 30. It was already about, it was already at, I'm looking for the units. I don't remember what they are. Cubic feet. Okay, so t was already at 30 cubic feet, or the amount was already 30 cubic feet when we started. So we've got to add this 30 in here. 30 plus whatever we got from 0 to the time that we're talking about. Okay, and again, you can use, if you save them in your calculator, you can just plug in y2 and y3 or whatever numbers they are for you there. You're on the AP test, though, they do not care about this notation. So do not write this as part of your answer. That can only help you in the calculator. They see y2, but they don't know what y2 is in your calculator. The readers don't know what y2 is. They only know what r is. So make sure you're using this notation, but you can use this just in your calculator. Okay, so again, not going to take too much time to go through this because I want to make sure we get to the end of this problem. All you would be doing was taking t, substituting that in for your top bound, okay, so that we can get the different values, the different amounts. So 0 is not a bad one. 0 to 0 means that this whole integral is going to become 0, and so we'll have 30. When you plug in 3.271, you get about 27.965. And then when you plug in 8, you get 48.543. Okay. And so what was our question again? Our question was, what is the minimum? And let's make sure we're reading that right. Our question is, at what time? Okay. So again, important to interpret your question It's asking what time is the minimum. And so let's look back. The time of our minimum is 3.271 hours. So our minimum of 27.965 cubic feet of water occurs at T equals 3.271. That's our like final synopsis for our reasoning for our answer. Let's take a look at how this was graded. I think this one, the answer was so big I had to cover the question. Yeah. Okay. So yeah, so they talk about the amount of water here that they're going to need to use later. They look at RT minus D of T, and that when that equals 0, that's 1 point right there, considering that this formula, this rate combined, is going to get you what your actual rate of them together is, because your D of T is what is leaving. So when that equals 0, we found those two values. We use the table to find the endpoints as well as the critical points. And then your final answer, which is 3.272 or 71, and with a justification. And I believe this table, coupled with the sentence down here, counts as your justification. Okay, so you doing this test has justified that this amount of water will be, or sorry, this time will show you the minimum amount of water. All right, 7:26, we've got part D. Hopefully we can get through that in this last 4 minutes. Okay, the rate at which rainwater flows into a drain pipe is modeled by this. Same question, we're good with that. So we've got the pipe can hold 50 cubic feet of water before overflowing. When T is greater than 8, the water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Okay, so it's not overflowing until it hits 50 cubic feet. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe begins to overflow. Okay, so with this one here, a few things to consider. We know it has to be an equation. That means we're going to have an equal sign in there. You're not just writing an integral. Make sure that you have the equation in there. Let's take a look at how we can write this to make sure we include everything. Okay, so we were told that it can hold up to 50. So our maximum amount we can get to is 50. So that's going to have to be in our equation somewhere. We also know that we started with 30. So we already had 30 in there when we started. This place is kind of the ambiguous part, and we're looking for an equation that gives the time W. So it's telling us to use W here. If you don't use W, it is not going to be the correct response. So we're going to add this to, and again, we're just looking for the amount of water, similar to what we were looking for in the first one. Or sorry, in the previous one, the amount. So we're just going to need an integral with how much is left after R of T and D of T are done, depending on whatever time. And I didn't leave enough space here. This should have a dt in there. So you've got 30 plus the integral from 0 to W, because that's the variable it gave us, of R of T minus D of T with respect to T. And whenever that equals 50, that's your cap. So whatever W is, when you solve for W, that would tell us when it overflows. But we don't need to solve this. We only needed an equation. So if we look over here, you got 1 point for that correct integral and 1 point for the equation. So again, not too much to write out on this one, but again, being very careful of your interpretation, making sure you remember that you have to add that 30 as well. All right, take a breather, get a drink of water. I'm going to get started by showing you this problem. Take a second to read it. We've got 3 parts here. This is from the 2014 exam. It's question number 2. So again, it is a calculator active question. You might have seen this equation in my calculator just a minute ago. Okay. So we've got a function here, f of x. And this is what's representing f of x right here. And then we've also got the horizontal line of y equals 4. That's our straight horizontal line right there. It says figure above, but it's to the side. I'm not sure. I copied this from the scoring guide, so maybe they just didn't. It was above on the exam, and now it's to the side. Okay, so for part A, we need to find the volume of the solid generated when r is rotated around the horizontal line y equals -2. I'm really glad we're going over this one because this is not around the x or y axis, so we need to be careful to make sure we find the correct radius. And then for part B, we're going to look at the region R, which is the base of a solid that is cross sections. And so we're going to be looking at triangles coming out of that, isosceles right triangles. And then we're going to use a vertical line at x equals k, could be anywhere, but it divides the region into 2 equal areas. And again, we end up with this write but do not solve, an equation involving integral expressions whose solution gives the value of k. All right, let's get started on A. One of the probably more difficult parts of A is just first visualizing what this is going to look like. And when I do this, I have to draw this out. No matter how many times I've done a problem like this, it's always helpful for me to draw it out. So let's take some time here to draw this out. I suggest you do the same. So we're going to look here. Our original piece is at y equals 4. And say this is the x-axis right here. And so we're like up here, and then we have a little plateau right there, and then we go down further, and then we go back up right here. And we don't know any of these other values, but we know this is r right here. And it says it's reflected about the line y equals -2, I believe. Let me check. Yes. So let's say -2 is like right here. And so we're reflecting this shape across this line. So I'm saying, okay, well, if this is at 4, this like plateau inflection point here, that is 6 away from -2. This is a distance of 6. And again, you don't really need to be doing this in total this much detail, but this really helps me a lot to make sure I'm drawing it correctly. So if that's 6 away, I'm going to be down here at -8 is kind of the reflection of this, where it's going to be. And so it's going to be something like this. And then it's going to go in and then out. So again, I'm kind of just looking at this line as my reflection point. It's like a mirror on either side. Of course, I didn't draw it perfectly. Not an art teacher either. Told you I'm not an English teacher, also not an art teacher. There's reasons I'm in math. And then so we're looking at this shape here. And the best comparison I can have for this shape is it kind of looks like, you know, those like hourglasses you use when you play games that the sand falls through, right? Like there's sand falling through this piece. It's just kind of turned on its side. And we're looking for this shape, the volume of the solid when it's generated around y equals -2. Okay. So when we're looking for volume, we know that if we were looking at this from the side, like say we took this and we turned it towards us, it's just going to be a collection of circles that have different diameters, different radii. And so we're looking to just integrate the area of a circle in order to find the volume. So volume in general, we're looking to integrate pi r squared. We're looking to integrate the area. So we need to find r. What is r? Well, let me remind you, we know f of x, this function here that we have, is x to the 4th minus 2.3x squared plus 4. Okay, and so we're just going to refer to this as f of x when we're writing it down, just to make sure we're consistent with what we're doing. And we want this radius. We're looking for use a different color. We need to find r of this shape. And so if this is our point of turning, this is going to help us find r. So r is whatever this distance is here, or this distance, it's going to be changing, or this distance. This is our r. So how do we know what this is if this is changing? Well, we can use f of x to help us with this. We know that this distance here represents f of x. This distance here represents f of x. This distance here represents f of x. All of these distances, regardless of what they are determined by f of x. But that's not our whole radius, right? We still have this extra piece of purple line right here, this extra piece. But lucky for us, this piece is not changing. This piece is just 2 extra. No matter what f of x is, this piece is 2 more than what we had. So this helps us find r. Okay. And we also know that this right here, this is our like outer function here, right? That's also determining for us. This is 4. And so we want to take out, we want this piece right here with this subtracted out, this region of r subtracted out from both pieces. So we also know that this radius is going to be a distance of 4 plus 2, right? 6. So when we look for what r is, it's got a few components. Okay, we're looking again for this inner hourglass piece. And so what we do is we take the integral, we've got pi, a constant there, and we say, well, we know the outer piece is our radius of 4 plus 2 extra because we're at -2 here. And again, that's why it's important to draw it out. You see -2, you might think we're subtracting 2, but that's 2 farther away, which means in terms of distance, we are taking 4 and we're adding 2. Okay, squared, we're taking this radius, pi r squared, minus, and we want to subtract out this r right here. And that r is made to us by pi, and then the radius for this one is our function, tells us our radius, but we have plus 2 because of this extra piece here, again, and that's squared because it's pi r squared, and then dx. Now, everything so far looks really good. We're integrating all of this with respect to dx. The only problem here is we haven't found any bounds yet. We don't know what this and this are. Okay, and so this is where the fact that this is a calculator question comes in handy. So again, we've taken this outer piece, we've subtracted out this inner piece to get this piece right here, the hourglass piece. And now we need to make sure to find the endpoints, which are going to be determined by, move this down a little bit, determined by this piece here and this piece here. Okay, so let's take a look. So I've already got our first function in here, so I'm going to turn that back on. We've used these already, so I'm just going to get rid of these. And then I also want 4. I need y equals 4 in there, and we'll see why in a second. So let's graph this. Okay, so you can see we're only seeing that little piece of this function here. We could zoom in a little closer. Again, I don't want to spend too much time on just this calculator portion. So the point here would be to find the intersection points, the 2 places where y equals 4 intersects with our function right here. And that, again, is in second trace. Intersect. We can find one of them just to make sure you know how. So it's asked for the first curve. Let's say we want to find this one on the right. I just go really close. It's on the blue one. That's our first curve. Now it's on the red one. Could go left and right, but I'm pretty close already. So I'm going to hit enter. That's my second curve. And that's its guess, but I'm going to hit enter one more time to find the intersection, and it happens at x equals 2.3. Okay, so our upper bound, this is our farther one, is 2.3. And our lower bound, which I didn't show you, is 0. Okay, so if they intersect, you've got 0. They intersect at 0, 2.3, and now we've got this beautiful integral that you can use your calculator to integrate. Again, plugging in, plugging it into where the function is in the calculator, the y functions, and then using that in your calculator can help you from making so many small errors when you're typing things in. So that's something I always advocate for, is simplifying as much as you can before you plug it into that last step in your calculator. Okay, so when we do this, we get the volume to be 98.868, and then it could also have been 98.867. AP will accept both of those. All right, let's take a look at the answer for this one. So we got that f of x equals 4 at 0 and 2.3. Those are the endpoints. They pulled pi out here. That's totally fine. You could do it the way I wrote it or the way they did. That's not going to change anything. But that integrand on its own is 2 points. That's the most important part. The limits, 0 and 2.3, those were another point, and then your answer was just 1 point. So you could have found the correct limits, found the correct volume formula, and then if something happens along the way, your answer is a little bit off, you still get 3 out of 4 points. And again, you want to make sure you're getting those 4 out of 4 points and any errors are not just in that last step. But I think it's very good to know that it's not all about the answer. It's all about knowing that you know the process. Okay, part A. Again, if you have questions, please put them for Pooja and JP. Actually, Pooja might be with BC now, so JP in the discussion threads. So that was part A. 2 more parts to go with this one. Okay. So same problem, but now we've got B. Region R is now the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle. That shape is important. It's the most important part of this. With a leg in R, find the volume of that solid. So again, for me, drawing this is so important. So I'm going to draw it again. Give you guys a minute to look at the question while I draw that. Okay. And we want to find cross sections. We want to find volume. And then, but our cross sections are isosceles right triangles. Okay, let's take a look. Okay, so I'm going to try to draw some of these isosceles right triangles here, just so I can kind of visualize this. It said it had a leg in R, which means that one of the isosceles pieces, one of the legs, is R. So let's try a small one here. So let's say we've got one here, and then the other leg is right here, and then this is the hypotenuse. So you want to picture this like coming out of the page. This is like A, B, and C, and it's sticking straight up. And so this region R, its volume is just made of tons of these isosceles right triangles. And the important part about the isosceles is that this and this are the same. This and this are the same. And we could keep doing this. We could make one here. Again, pretend it's standing up. Well, this one is standing up, so it's going to go, looks like it goes past our function, but it doesn't. Just trying to draw somewhat to scale. Okay, so those are again equal. So now we're like, okay, we know that the base of R and the height of it are going to be equal. We've got the right triangle, we've got the isosceles part. And so all of these, picture these all stacked up next to each other, all coming out of the board. Okay, I do an experiment with my class where we use Play-Doh, and we just kind of make the shapes out of Play-Doh and stack them on top of these. It works pretty well. So now whenever you're doing cross sections, the way you decide what your volume is, how to find your volume, is you integrate. It's always the area of the shape you were given, right? So we were given an isosceles right triangle. So we're going to integrate the area of that shape. And we can use some information that we've already found here. We know that this is 0 and this is 2.3. And so now let's look at integrating this. The integral from 0 to 2.3. And so now again, we want the area of the shape. In isosceles right triangle, what a triangle has an area of 1/2 base times height. So 1/2 is a constant. We'll just put that in as 1/2. Base times height. Well, we know that base and height, because it's isosceles, these are the same. Okay, same because it's isosceles. But what are they? What is this length here? And again, we're going to have to look at it in the relationship between 4 and our function f of x. Okay, so f of x is going to tell us this distance here. We don't really want this distance. This is the part we want. We want the piece that's left that's between 4 and after this is taken out. Okay, so 4 is this whole piece, right? This is a whole height of 4. And this piece right here is whatever f of x is. So in order to figure out the base, this little piece in here, we say, okay, well, we've got 4 total. And if we take out f of x, if we subtract out f of x here, we will end up with just what's left here, our base value, which is also our height. Okay, so I'm going to take that, and base times height, I know they're the same. So I'm going to just take my 4 minus f of x, and I'm going to square it. That represents base times height being the exact same, means we can just square it instead of having to write it twice. And now we've got this nice integral to represent this little space in here times this space up here, which are the same because it's isosceles. And again, you're going to use your calculator at this point, plugging in this function here, our function for f of x that is on the previous page, same bounds, and solving here. What you should end up with is about 3.574, and again, or 3.573. They don't care if you truncate or if you round, as long as both are legitimate to 3 decimal places. Okay, let's take a look at this one. So here, 2 points for that integrand that we made, 4 minus f of x. Again, that's probably the most difficult part. The area of an isosceles right triangle, you know that's 1/2 base times height, but can you recognize, I'll draw it again in here to make sure it's clear. Can you recognize that in order to find this distance here, you have to take this whole distance, which is 4, and subtract out this distance here between your curve and your x-axis, which is going to represent your function. That gives you just this little piece left in here, which is what we're looking for. Awesome. Hope you guys are following along. Take a deep breath. You are over halfway, by the way. We're at 7:50 right now. We're going until 8:30, and then you've got an hour and a half left with Jamal. So let's keep going. We've got part C of this question, and then we've got one more after that that we're hoping to look at and finish. Okay, the vertical line, x equals k, divides R into 2 regions with equal areas, and we want to write but not solve a formula for k. Give you guys a second to digest and think about this one. Ask any questions on the previous one while I draw out this shape. Okay. Okay, so we're looking for a K that divides the area in two equal parts. And we want an equation, again, involving integrals. So it's giving you some hints here. An equation, it has to have integrals. And it involves a solution that would give you K. That means K should be your only unknown. Okay, let's try it out. So first, I want to think about how I would find the area of this entire thing in general, right? So how do we find the area of a shape? Well, we integrate the function, right? That in order to find area, we integrate f of x. That's how the distinction we have where integration is area, and we can go back and forth with those. But if we just integrated f of x, again, we'd have this problem here where that would get us this piece. And that's not what we want. We want this piece in here. And this piece is a connection between 4 and the function, but it's the other side of the function than what we're used to looking for. We want this piece in here. And so in order to get this piece here, we're going to take the integral. And again, we found those endpoints. Luckily, they've been useful to us throughout this problem. We haven't had to re-find them. 0 to 2.3. And now, again, we're looking at finding this area that's below 4, but above our function. And so we have 4 minus f of x again. That would find this entire area here. Now, again, it's important to realize that because we're finding area, this is not part of a formula. When you're finding volume, you're integrating an area. When you're finding area, you're just integrating a function. You're not integrating any extra formula within that function. But in this case, we want an equation that would help us with K, where it divides it into 2 equal parts. Knowing that it's in 2 equal parts is actually helpful, because can't we say, okay, well, that's what's going to be on either side of the equal sign is half and half. So we're looking for some value K in here that splits this in half, and we don't know what it is. We know that this is 0 and that this is 2.3, but we don't know what K is. It says we need to use integrals. It says it needs to be an equation, and it has to have a solution. And so all we're really doing here is thinking, okay, well, we don't need to find this. We don't need to find K. We just need to think about how could we make an integral that shows them at equal parts where K has split them in half. Well, all we have to do is split the integral at K. We say from 0 to K of this function, that would give us 1/2. And that's going to be equal to, dx. That's going to be equal to whatever K to 2.3 is. That's our other half of the same function. And here's our formula. From 0 to K of 4 minus f of x is going to be equal from K to 2.3 of 4 minus f of x. This is the first half, which is going to be equal to our second half. Let's take a look at how AP Calc scored this one. Okay, 1 point for the area of one region and 2 points for the equation. So even if you had only found half of this, they still found a way to get you some credit. Even if you weren't sure if K mattered on both instances, AP was like, well, they had the idea there. We're going to give them some credit. So I do appreciate that AP does that. And then the full equation, the final answer, gets you that second point. All right, that's our free response question on area and volume. A lot of times there is one on area and the volume on the exam. And this one, again, was in the calculator section. This could be in either section. I think more likely a little bit in the calculator section if you're getting equations that look like this. If they were to put something like this in the non-calculator section, they would be giving you a function that you did not have to do all this, like the tiny algebra steps out to integrate, because that takes away from the calculus. They're trying to assess you on your calculus, not on your algebra. All right, we're going to move on to our last, maybe last, if we have more time. I'll see if I have one backup just in case, but maybe last question of the night. And that's going to be somewhat of a table and chart problem that involves the existence theorems. So we're going to start this next problem with a review of the 3 existence theorems. Oh, I forgot I went out of order, so hang on. Yes, as you can see, we've got a very big slideshow for you here. All right, here we go. So we've got 3 existence theorems. We've got the mean value theorem, the intermediate value theorem, and the extreme value theorem. The mean value theorem, which is right here, may be one of the ones we use the most and apply the most. And the mean value theorem tells us that if we've got a continuous and differentiable function, and remember those conditions because you can't use mean value theorem without it, on this open interval AB, then there exists at least one point C, this is point C right here, such that the derivative at C is the same thing as the average rate of change between A and B, 2 other points on that line, as long as it's continuous between them. And so the way I like to put the mean value theorem in terms that makes the most sense to me is that the slope, the instantaneous rate of change, the instant slope at an instant, is the same as the average slope of 2 other points. And you can see that this would work in other places too, right? As long as the function is continuous, I could say that this is A and B, and I could find a line somewhere, that's not it, somewhere that has a similar slope to what I chose for A and B. And so it's really saying that a tangent line, this is a tangent line, can be equal to a secant line. Well, yeah, as long as it's continuous, you're always going to kind of be able to curve both of them together to get them to be at the same, continuous and differentiable, to get the same slope out of them. So again, I just think average slope equals instant slope, and that's how I remember mean value theorem. And again, mean means average, and that's another way to help you remember it. Okay, next, here's a slide for the extreme value theorem. So we've got a function f is continuous, and it's on a finite closed interval. So notice here, it doesn't need to be differentiable. It only needs to be continuous. And if it's continuous on that finite and closed interval, so that finite closed part is important because that means it has endpoints. Then on f, there exists both an absolute maximum and an absolute minimum on AB. Yeah, there has to be a highest point and a lowest point. Even if it's a straight line, that means the highest point and the lowest point are the same point. Last theorem, intermediate value theorem. If f is continuous on a closed interval AB, so again, only continuous, doesn't matter if it's differentiable, then there's some number k, that's a y value. It's between f of a and f of b, inclusive, so including f of a and f of b. Then there exists at least one number x. So if this is continuous, that means if I have a k value that hits my graph, there's got to be an x value between a and b, such that if I plug x into f, I get k. So it's saying that k is f of x here. And again, if your function is continuous, there's no way for this not to happen. I remember when I first learned about this as a student, thinking, why do we even have to talk about this way? How is this not something that I didn't even know another way to explain it? But then it's beautiful how simply it explains something that is hard to explain. But anytime you've got a value of y that's in between 2 other values of y on a continuous function, there's got to be an x value in between the 2 other x values that map to those first y values, that when you plug that into your function, you get that y value that you wanted at the beginning. Whew. That's the intermediate value theorem, one of my favorites. Now, the theorems can sneak up on you on the test. They could give you a problem that all you need is to use one of the theorems, and if you don't recognize it, it may seem like a problem that you're like, I don't really know what they're asking me to do or how to solve this. So it's really important that you recognize and see when it's trying to compare things about the intermediate value theorem, the mean value theorem, and the extreme value theorem. The mean value theorem, whenever it asks about some average rate of change and mentions a derivative, your first thought should be thinking about the mean value theorem. Whenever it talks about something being in between two y values, your first thought should be the intermediate value theorem. Try that first and then go from there. With the extreme value theorem, this more comes up when we're doing things like the maximum and minimum problem we just did when we did a rate in and rate out problem. So when you're looking for the extreme value theorem, it's kind of more, I feel like it's more intuitive when to use because it's asking you for a maximum or minimum usually. But sometimes they do give you one where it's just asking, why is this true? And it's because of the extreme value theorem, but that probably won't be part of a free response question. You're more likely to see the mean value theorem and the intermediate value theorem when it comes to a free response. All right, my last half hour, let's look at this last one here. Okay, so this one again involves the existence theorems and the use of a chart, which I just went over in a previous stream in April, one of the free response review streams. Okay, so we've got F and G, and we're told they're differentiable. That's good because remember we have conditions. And G is strictly increasing. And we've got values of F, F prime, G, and G prime for 1 through 4. And then it tells us about this H. It says H of X is F of G of X minus 6. Okay. Part A, explain why there must be a value R between 1 and 3 such that H of R is -5. Okay. So this one, I know I said it out loud. It wasn't written here, but I said between 1 and 3. And you're looking for an R such that H of R equals -5. This is all just talking about the function. I'm thinking just from the beginning that maybe this one involves the intermediate value theorem. This one here, explain why there must be a value C between 1 and 3 such that H prime of C equals -5. Okay, I see H prime. Now I'm suspicious that this is going to be the mean value theorem, right? I don't have an average value, but I've got a table. And usually when I have a table, I can use average value to prove that the mean value theorem is useful. All right, and then here we're using a derivative. This one we might not need, we don't need the theorems for all of the parts. It's mostly just the first two. We'll take a look at that, but we are going to do all 4. And so this one, we're actually going to be using a little bit of the fundamental theorem of calculus, making sure you remember how to take the derivative of something like this. And then lastly, for D, we're reviewing inverses of derivatives, which is always good to review. So let's look at part A. And again, I'm thinking intermediate value theorem here. But in order to use the intermediate value theorem, I have to figure out for H of X, I've got to find a value that's larger than -5. And a value that's less than -5 in order to be able to say that I can use the intermediate value theorem, because I have to say that it can be in between 2 values. But this is talking about H, and we don't know any of H's values here. So let's start by figuring out H of 1. H of 1 is going to be F of G of 1 minus 6. Okay, so we've got G of 1, which is 2. So we've got F of 2. So this, I'll write this first one all the way out, but then the rest I'm going to show you. So we've got F of 2 minus 6. This is an arrow. And then F of 2 is 9. So we've got 9 minus 6. And so we get 3. So when X is 1, H of X, according to this formula for H of X, is going to be 3. And I found the other values for you. At 2, it's going to be 4. At 3, it's going to be -7. And at 4, we actually can't figure out what it is because we end up with we end up with f of 6, and f of 6 is not in this table. So we must not need it. We can't figure out what it is. But we found what we're looking for. This value, so we've got h of 1. H of 1, we have 3. And h of 3, we have -7. Well, that's what I wanted because I wanted -5 to be between two of the other values. And look, we use 1 and 3 here. So again, 4 really didn't matter. We've got h of 1 and h of 3 are two endpoints. There's one thing we're missing here in our description. In order to use the IVT, which it's looking like I can use, I can say, well, yeah, if the function goes from -7 to 3, or from 3 to -7, doesn't matter the order, then somewhere along the way, h of r is going to be -5 because of the IVT. But your answer would not be complete at this stage. Don't forget, in order to be able to use the intermediate value theorem, you need to mention that it is continuous. Because f and g are both differentiable, that means they're continuous. Because h is made out of f and g, that means h is also continuous. Okay, so we need to make sure to remember to write that h is continuous. H is continuous. And so this one, I didn't write it out on paper. It would have taken me probably a while if you just watching me to write out this explanation. So I wanted to just show you a little bit on here, and then we're going to look at exactly how AP describes this answer here using the intermediate value theorem to make sure we bring this all together. Okay, so they find h of 1, they get 3. They find h of 3, they get -7. That's a point right there. Then, since h of 3, since is a good word to use, by the way, when you're starting a sentence. Since h of 3 is less than -5 is less than h of 1, so that's that statement of the intermediate value theorem. And h is continuous. Okay, so again, you need to remember the conditions. This has to be true. K, this is our K. It's between f of A and f of B. It's continuous. That's our condition. So now that we know these two things, we can now say that by the intermediate value theorem, this is true. And we just rewrite that at the bottom here. There exists a value r between 1 and 3 such that h of r equals -5. Okay, and that's 2 points. Again, conclusion using the intermediate value theorem. So it's important to make sure you are writing out these conditions. If you have not written out the conditions, you're not going to get full credit. Again, that's part of your conclusion. If you don't prove that you can use the intermediate value theorem, you cannot get credit for using it. You guys are doing awesome, by the way. It's at 8 o'clock. We are exactly, well, actually, we're 8 minutes over, 3 hours in. 8 o'clock for me, my time. And let's keep going with this problem. Okay. Same problem, but now B, explain why there must be a value C between 1 and 3, such that h prime of C equals -5. So again, when you see this, when you're asked to explain something about a derivative on an interval that you have in a table, you automatically want to be thinking mean value theorem. You see an interval you're between in a derivative and explain, you should be automatically thinking mean value theorem. Okay, so this one I'm going to use paper to write out. So I know that I want to show that h prime of 3, sorry, was it 3? Let me make sure. Sorry, h prime of C equals -5. C, 3 is an endpoint. And then we want to know that, we want to explain why we know this. So how do we know this? Well, if we can use the information we already have to show that the average rate of change is true, we can use the mean value theorem. So first of all, let's start with the conditions. H of x is differentiable. We know this because it's made of f and g are differentiable. Okay. So now let's look for the average rate of change. Average rate of change using what we know in the table. So if these are our endpoints, let's start by using those. H of 3 minus H of 1 over 3 minus 1. So if this comes out to -5, that tells me that I can use the mean value theorem here. So these were found in the last problem, right? H of 3 was -7. H of 1 was 3. -7 minus 3 over 3 minus 1 gets us -10 over 2, which is -5. Okay. So that's good. That's what we wanted. We just found an average rate of change using two endpoints that has a value, and this is the important part, that it has the value that matches what it wanted us to find here. If we didn't get -5 here, we can't say anything about the mean value theorem because it needs to match in order to say that it's true. So we want to write that since h of x is differentiable, since h of x is, let's say, continuous and differentiable, right? We have those two conditions for mean value theorem. And you might think, well, if I write it's differentiable, that means it's continuous. AP still wants you to write them both out. Okay, so h of x is continuous and differentiable. Then by the mean value theorem, there exists a C between 1 and 3 so that h prime of C equals -5, because h of 3 minus h of 1 over 3 minus 1 equals -5. Okay, so you need this part in order to say that this is true. You need to have shown this somewhere in your explanation. Oh, sorry, let me give you a second to digest that, take a look at that answer. Again, we're looking to make sure that we've got everything written that AP wants. You don't want to spend too much time writing things that you don't need. But if you forget to write these conditions, you do not get credit. So it really, you will benefit from taking a little extra time to make sure you've written the conditions, make sure you've related it back to what the question was asking, and making sure your answer is complete. Okay, so let's look at AP's response. They found the average rate of change between 3 and 1, and they got -5. And they say since h is continuous and differentiable, again, they spell them both out here, by the mean value theorem, there exists a value C such that C between 1 and 3, h prime of C equals -5. Awesome. So here they didn't even ask, I wrote because and wrote why. That is fine, but apparently you didn't need it here as long as you showed this up here. As long as somewhere you have shown that the average rate of change is going to get you -5, you're able to use the mean value theorem if your function is continuous and differentiable. So that's part B of this problem. Again, really important to make sure you're interpreting exactly what it's asking for. It's talking about H, it's not talking about F or G, but F and G are both involved, and the fact that they are differentiable is very important. Okay, let's look at C. Also, I love that the captions up here thought I said the word C, S-E-A. I'm talking about the letter C if you're reading these later. Okay, for this one, we've got W. It's the function from 1 to g of x of f of t dt, and we're finding the value of W prime of 3. Okay, so this goes back to the fundamental theorem of calculus, the part we use a little less often. It might have been a while since you've used something like this, or maybe not. Maybe you've used it recently. Let's write down what Wx is. The integral from, it's 1, correct? 1 to g of x of f of t dt. And we want to know what is w prime of 3. Okay, so the fundamental theorem of calculus, the first part tells us about how, or it depends. Actually, I had a textbook that said this was the first part and a textbook that said it was the second part. But one of the parts talks about how you have the integral from a to b of f of x dx, that is f of b minus f of a. And that is the really popular way that we use. But the other way that comes up somewhat often is also how to use a function that, or an integral that goes from 1 to a function or a variable. And when you've got the integral and you're looking for the derivative. And so when we take the derivative of this integral here, when we're looking for w prime of x, usually when it was just x up here, all we would have to do when we're looking for the derivative of an integral, because those are opposite operations, it basically cancels out. I don't really like using the words cancels out, but I'll say that for now. Basically cancels out what's integrating and then deriving. And so you're just left with what this is once it is plugged into here. This constant, once we take the derivative, would have become 0. So we're just left with f of g of x. But remember, you did just take the derivative of this. So you also have to multiply this by g prime of x. So if you're looking at this and you're not sure what just happened, let me write that out for you. I think we've got a little bit of time here to do that. So if you want the derivative of an integral, and we do this, if we do this step by step, this is g of x. First thing we do is take the integral. The integral, using this first part of the fundamental theorem, would be f of g of x minus f of 1, right? We take our two endpoints and we plug them in. Then we take the derivative. The derivative of f of 1 is just 0. The derivative of f of g of x brings us back down to little f of g of x, so that's the derivative of f. But then remember, chain rule here says we also have to multiply it by the derivative of g. So while it looks similar to the regular chain rule, it's a little bit different because there's no prime up here with the f. It's f of g of x times g prime of x. And we just got that from doing that out there. Okay, and now we want w prime of 3. And so from here, this shouldn't be too bad. We've got a chart that's telling us what all these values are. So we've got f of g of 3 times g prime of 3. And so let's go take a look back at that table. Okay, f of g of 3, let me just write that on the side over here so we remember what we're looking for. F of g of 3 times g prime of 3, and that's going to tell us what w prime of 3 is. So f of g of 3 is the same thing as f of 4, because g of 3 is 4, times g prime of 3, which is 2. Okay, now we find f of 4. We get, this is the same thing as negative 1 times 2, which is negative 2, which is w prime of 3. Okay, so this is not the first time we really used the table, but this is the first one that didn't really involve h in terms of our problems. A and B involved h and using the two theorems. This one we didn't need a theorem for, but we did need to remember the fundamental theorem. So we needed a different theorem, just not an existence theorem. And again, the more difficult part of this is figuring out what this derivative would be and remembering to multiply it by this g prime of 3. Once you have that, you plug in the numbers as you go using the table. I'm always very careful about making sure I'm looking, okay, g of 3 is 4. I kind of draw myself fake lines between the two, or if you're on a paper test, actual lines. Okay, that's part C. We are moving on to part D. And if you remember, part D was about inverse functions and inverse derivatives. So I'm just going to give us a little refresher before we go into that part. Take a look at this slide here. This slide gives us the formula for the derivative of an inverse function. And so there are a couple ways to do this. The derivative of an inverse, this formula, I would say if you know it, it's great to memorize it. If you're looking at this and you're like, oh, I do not remember this formula. If you remember how to find an inverse, which is to switch x and y and solve for y, a lot of times you can also use that as well. You can just find the inverse and then take the derivative of that. This is just a formula that's already gone through that process. And if you can memorize this, you don't have to remember to always find the inverse and then take the derivative each time. So we're going to be using this formula to help us with our next problem. I'm just writing it down on my paper to make sure we have it ready to go. Okay, well, almost gave you the answer there. Hopefully it wasn't fast enough that you could read it. Okay, so same beginning to the problem, but this time we have g negative 1, the inverse of g. Write an equation for the line tangent to the graph at x equals 2. So tangent to g negative 1 at x equals 2. Okay, I've done this before, but I'm going to go about how exactly I would start this problem. And so when I think, this is kind of like my thought process. So I'm going to put it over here in a thought bubble because writing this on the test will not help you. I think I hear a tangent line. I'm automatically in my head, y minus y1 equals m times x minus x1. But this is an algebra formula, and we have different names for all of these things now, according to what we are doing in our calculus problem with, in this case, an inverse function. So then in the problem, I would interpret this to be y minus, well, y1, our y in this case is our inverse, because that's what we're finding the tangent to. And it's at x equals 2. So y1 is going to be g inverse at 2. Equals m stands for slope, which in calculus means derivative. Derivative of our function is going to be the inverse derivative. And then we've got x minus x1, in our case, is just 2. That's where we can just plug in the x and not have to worry about anything else. Okay, so y we don't need to look for, x we don't need to look for. The two things we need to find are inverse, g inverse of 2, and g inverse prime. Oh, sorry, I should have plugged in a 2 here as well. This is a 2. There we go. Okay, let's start with g inverse of 2. We know that in the original, if g of something equals 2, that means that in the inverse, g of 2 is going to equal whatever was in here. So we need to figure out what value of x in the original, sorry, this is inverse, makes it so that the inverse inputs 2. What would we get? So let's go back to our table. And we're looking at g, and I'm looking for where is g2. I don't have to look very far. It's the first point here. So we've got 1. So we know that g of 1 equals 2. So that means g inverse of 2 is going to be 1. So we've found this value. It is 1. To find this value, g inverse prime of 2, we're going to need this formula here, but in terms of g. So g inverse prime of 2 is going to be 1 over g prime of g inverse of 2. So I just plugged in 2 for x. Use the same formula I've got here. There is a prime up there. It's kind of hard to see. That is a prime. Okay. And okay, so good. We already know a lot of this information. So let's use g inverse of 2. Remember, we always start at our inner function, work our way out. G inverse of 2 we just found. It's right here, 1. Make sure you're not refinding information that you already know. We get g prime of 1. Okay. after g prime of 1. Now we need to figure out what is g prime of 1. I did not have that. Wasn't sure what that was, so we got to go back here. We do have g prime. Now we're using the actual g prime. We're not looking at an inverse, so we're looking for 1, and 5 is going to be our answer here. And so that's an important thing to know, is that we're just looking for g prime at 1. We're not looking for the inverse. So it can be very tempting to see, ooh, 1, it must be 2. No, that would be an inverse function. So g prime of 1 is 5. We already took care of the inverse piece with this part. And so we get 1 over 5. And this, again, stood for g negative 1 prime of 2. Okay. So now let's put this all together. The whole point was to find a tangent line here. So we've got y minus 1 equals 1/5 x minus 2. And we can just leave it here. This is our equation of a tangent line. I shouldn't put an equal sign there because I'm just writing a statement about it. Tangent line to g inverse of x at x equals 2. And we don't need to simplify this anymore. And then another tip, just as you're thinking about the exam and going back into the exam in general, on the free response questions, anything that's already in algebra, you don't have to simplify the algebra all the way. That's where easy mistakes can happen when you're looking for that specific answer. If you have something that's like 3 times 2 plus 6 divided by 5, you don't have to simplify that. As long as all the numbers and everything has been plugged in and you haven't left anything unsolved besides just the last algebra, you are all set. Make sure you're solving any functions that are still in there. You should not be leaving any functions as part of your answer. All right, let's go back and see how this was scored with AP. So they did something very similar. They've got g of 1 equals 2, so g inverse of 2 must be 1. That's the first thing they're looking for you to get. They're also looking for you to get the inverse derivative. That was 1/5. And then lastly, they're looking for you to put that into your tangent line equation form to get that. Awesome work, you guys. I haven't seen any questions in my phone. I hope everything's going well there in the discussion threads and you guys could see and hear everything okay. We're just about to wrap up here. Let's just do an overview of what we just went through because we've got an extra minute or so. So we did, it's easier if I just go to the slide here. Okay, so we did an area volume problem. You can find that on the Unit 8 cram. We also did a rate in and rate out problem. This was actually the first one we did. You can find that in some of the free response question crams. I did this, I believe actually the first free response question cram we did. And then we also reviewed the existence theorems, but not only the existence theorems, also how to use a table and chart. And you guys are now just about, you have an hour and a half left, so 3.5 hours in. You guys are going strong. Great work with this so far. We have finished everything that I have for you. And so I'm going to be leaving in a minute or so. So you're not done. You still have an hour and a half. Jamil is coming back for the last hour and a half. Pooja, I think, is with BC. I'm not sure because I can't see the discussion thread, but JP is still here. So before I go, I just want to say thank you to you guys, our crammers, to Pooja and JP for your hard work, and to Jamil for working with me. And I want you guys to finish strong. It's the last hour and a half. Get that second win right now. Get ready to go. And as you go into the test tomorrow, I don't know if I was your AP Calc teacher all year, but if you have been with me through the fall class and through the sessions we've been doing in the spring, good luck tomorrow or whichever day you take it. Know that Pooja, JP, Jamil, and I are all here in the discussions, and we've got a way of communicating and talking back to you, whether you have a question on anything else. So feel free to reach back out. And just remember, you're doing great work. You just have to trust yourself tomorrow. Do your best. You've got it. Be confident in what you know, and you're going to do great. Again, you're not leaving yet. This is just me saying goodbye. I didn't want to leave without saying goodbye. And make sure you believe in yourself. I know you can do it. We've done it together. You've done a great job so far. Hopefully this is giving you a second win to finish out those last few problems with Jamil. That's coming up right now. I'm going to stop sharing my screen to just say bye and say thank you all for working with me this year. Again, feel free to reach out. I love working with you guys. And
Let's take a look at another really common example that we see on the AP exam, especially over these last couple of years. Okay, and this one involves properties of integrals. So in a problem like that, like this, you're going to be given a bunch of information about some different integrals, and there's a way to connect them all. And your job is to figure out how do we combine these integrals to get the answer that we want. So the first thing I suggest that you do is you kind of look at the one you're after, because we're going to try and match this best we can. And what we notice in this is that we've got g of x first minus f of x. And we also have an integral from 1 to 5. So we know that we get to somehow combine this information up here to try to get g of x first minus f of x. Now, what I see right away is I've got two integrals about with bounds of 1 to 12. So that's going to be how I can put these two integrals together because they have the same bounds. So the first thing I'm going to do is I'm going to work with this integral of g of x, and I'm going to isolate the g of x. So what this is saying is I'm really integrating from 1 to 12, and I've got a 1/3 g of x, and it's equal to 5. So what I want to do is I want to take this equation, I want to multiply both sides by 5. If I multiply both sides, multiply both sides by 3. If I multiply both sides by 3, I'll lose the 1/3 on this side, and then I'll multiply the 5 by 3 on the other side, and we'll get 15. So now we know how g of x and f of x act between 1 and 12. So I can start to build an integral that starts to look a little bit more like this, with g of x coming first and f of x coming second. So what I'm going to do now is I'm going to integrate from 1 to 12, and I'm going to put my g of x first minus my f of x. Because they have the same bounds in these given integrals, I can combine these two expressions, okay? So now what I know is that my integral of g of x is actually equal to 15. We just found that. And then my integral of f of x over these bounds is equal to 14. So I know this is going to give me 15 minus 14, which is positive 1. So now from here, what we've got to do is we've got to figure out how to go from our bounds of 1 to 12 to our bounds of 1 to 5. But properties of integrals say we can break up our integrals. So what we want to do is we can see that if we go from 1 to 5 and then 5 to 12, that's going to be the same as going from 1 to 12. So they've given me this integral from 5 to 12, but the problem with this integral is I've got the wrong order. I've got f of x minus g of x. So we got to rearrange this a little bit. What we're going to do in this integral is we're going to keep it from 5 to 12, but we're going to factor out a -1. And that's going to change the signs of the two terms in my integrand. So when I factor out that -1, I can write g of x first and f of x second. And that's exactly what we want to match it to the integral they're asking us about. This does not change the value of this integral. It's still -7. All I've done is factor out a -1. But what it does do is it tells me now if I multiply both sides by -1, this side will become positive, and this side will become positive. So now I know that the integral from 5 to 12 of my integrand is equal to 7. So now I'm ready to piece together the integrals, because what I know is the integral from 1 to 12 of our integrand f of x, g of x minus f of x dx is going to be equal to the integral from 1 to 5 of that same integrand f of x minus g, I keep saying it backwards, g of x minus f of x dx, and then plus the integral from 5 to 12 of g of x minus f of x dx. So because they all have the same integrand, we can break this up into pieces, okay? So what do we know? Well, we have shown that this first integral from 1 to 12 is equal to +1. We got that answer right there. So that's equal to +1. The second integral, this one from 1 to 5, that's really the one we're trying to learn about. That's the one the question's all about. So we're just going to learn as much as we can about this integral. And then we know this last integral from 5 to 12, well, that's the one we worked on up here. That's equal to +7. So from here, I am going to just subtract 7 from both sides. I'm going to end up with -6 equals the integral from 1 to 5 of g of x minus f of x dx. And that is almost exactly what I want. I've got the integrand in the right direction. I've got the right bounds. The only difference is I've got a 1/2 out in front. So now what I'm going to do is I'm just going to make use of very basic equation solving. I'm going to multiply both sides by 1/2. And when I multiply both sides by 1/2, I now have the exact integral they're asking us about, and it's equal to half of -6. That's going to give me an answer of -3. All right. So properties of integrals. Be prepared to be given some integrals and then using the properties of integrals. And that means breaking them up into bite-sized chunks like we did here, instead of going from 1 to 12, breaking that up from 1 to 5, and then 5 to 12, multiplying, pulling out constants. Any of those kinds of integral skills can be used. Okay. So hopefully that one makes sense. We're going to look at the next example. All right, Megan, thank you so much for all that help that you've been given all throughout the year. I know all the 5 students really appreciate you and the time that you've given and the expertise that you've lent them. We are now on the home stretch. We've got our last hour and a half before we wrap up today, and I'm going to take you to the end. And for our last hour and a half together, here's what we're going to be focusing on. We're going to be talking about, first of all, what I call a fundamental theorem of calculus free response question. I call it a super FRQ. It's going to be a little bit longer than you'll see on the exam, but what it's going to do is it's going to get you ready for every type of question that they might ask with that type of problem. Okay. Then we're going to turn our attention to separable differential equations. And then for the last half hour or so, we're just going to talk about common pitfalls to avoid on the exam and some test taking strategies and just some general things to be ready for tomorrow as you get ready to take that exam. Okay, so 90 minutes to go. Let's see how it goes. We're going to start right off with our super FRQ question. It's going to be a problem where they give us a graph of G, but it's going to be an integral defined function where f equals some integral of G. Now, one thing that I like to do when I see these problems right away is I just like to look at this and see the geometry involved. There's all sorts of geometry as we look at this problem. So hopefully that you'll be ready for that. You'll be thinking about the geometry. We're going to see how that plays in. We're going to actually just jump right in and start answering these questions today. Okay, so here we go. Without further ado. So in this first one, we're given, like I said, this graph of G, but the figure shows the graph G, which consists of 4 line segments in a semicircle. It's important that they tell you that because that means these are going to form the geometric shapes that they look like they're going to form. Okay, we can't always go by our eyesight. The AP exam, the College Board has to tell you so there can be no confusion. But that's what they're telling us, that these are the shapes that we think we see. And then we're told that we've got an interval from 0 to 15. And this problem is about a function, and it's going to surprise you. It's not G, it's about f, actually. And this is an integral defined function. So just some common things to keep in mind. When you've got an integral defined function, such as this one, where f of x is equal to an integral from 7, in this case, to x of the function g of t dt, some things to keep in mind. One thing that I promise you will come into play is you're going to need to take the derivative of this function. And the derivative of this function is going to be done using the fundamental theorem of calculus. If you did it out, what's going to happen is you're going to get a parent function, and then you're going to take the derivative of that parent function. And because this bound right here is x, it actually behaves very nicely. This becomes g of x. Okay, so this is going to be the derivative of f of x is equal to g of x. If this bound right here were not x, if it were anything else other than x, including a constant, you would want to use the chain rule when you take the derivative of that parent function. Okay, for the majority of the problems that we've seen, they're putting an x up there, so we're going to get f prime of x equals g of x. Okay, but again, if it's not an x, please do the fundamental theorem and use the chain rule to compute that. The next thing that you're usually going to need somewhere in the problem is you're going to need the second derivative. Well, f double prime of x is the second derivative of f. And now we know that's just going to be the derivative of g, so that's going to be g prime of x. I guarantee you that when you do this problem, these 3 equations are going to come into play. And when you turn in your exam, the person grading your exam, they are instructed to find where you wrote this down on the paper somewhere. They're going to be looking all over for it. It's going to be the first step into earning points into these types of problems. So please, when you do this problem, put it right up next to the graph, make it nice and big and clear so everybody can see it. Let the reader know that anytime you've got an integral defined function, you're going to get the derivative and the second derivative, again, by using the fundamental theorem. But if there's just an x up here, it works out just like you like. You're going to end up with g of x for the first derivative and g prime for the second derivative. Once you know that, you're ready to go. We can start working on this problem. We're just going to go piece by piece. This is kind of a long one because I wanted to show you every single type of problem they could ask you so you'd be ready for the exam. So in the first one, you're asked to find f of 14. F of 14 is using that integral defined function. That is the integral from 7 to 14 of g of t dt. This literally is a geometry problem because integrals can be thought of as geometric interpretations. So as I start to look at this one, what I notice about it is I've got a geometry problem and I'm looking for basically how to use this geometry starting at 7 and ending at 14. So starting at 7, ending at 14, here's what we're going to do. That means, let me just change colors so you'll be able to see a little bit easier. That means I'm going to start here at 7 and I am going to continue to integrate from 7 to 8, and then from 8 all the way to 14. That's all the way up to there. So we're talking about this region of the graph. Okay, that's what we're talking about. What I like to do right away is I like to just put the areas on my graph so I know what they are. So my first area here is a triangle with a base of 1 and a height of 2. 1/2 base times height is going to give me an area of 1 for this guy. When I come over here, I'm going to separate this into some pieces. That triangle is symmetric to the one I just saw, so that's also going to have an area of 1. As I continue to make my way across this shape, I could use a trapezoid, but for me, it's just a little bit easier to break this up into a rectangle and a triangle because I can compute that pretty quickly. The area of that rectangle, you can count the squares, or you could actually do base times height. Either way, you're going to get an area of 6 for that guy. And then as you continue, you've got this last triangle, which has got a base of 2 and a height of 2. So 1/2 of 2 times 2, that's going to be a region of 2 right there. So now that I know these areas, I am going to go and I'm going to compute this answer. And what I'm going to end up getting is, well, my g of t is, you got to be careful. It's positive for the first region and then it's negative for the next region. My d of t is positive for both, and that's because anytime the top bound is greater than the bottom bound, you get a positive dt. Some of you guys might think of that as integrating left to right, and when you integrate from left to the right, you're going in the positive direction. When you go right to left, you're actually going in the negative direction. What that does is it helps me figure out what my answer is going to be. It means this piece right here, I'm going to the right and I'm above the axis. That piece is going to be a positive piece. So my first piece of area is going to be positive. Then for the remainder, I'm still going to the right, but I'm below the axis. So the remainder of that is going to be negative results. Keeping that in mind, I can now find f of 14 by using the geometry. The first region right here is going to be given as positive 1. And then the next region is all going to be negative. So it's -1, -6, -2. That's going to get me -9. And I'm sorry, it's going to get me 9, but I've already taken care of the negative. So it's going to be 1 minus 9. That's going to get me a final answer of -8. So my first answer, f of 14, equals -8. Okay, and that is done by using the integral defined function and using geometry. If you see geometric shapes in a problem like this, you will use them every single time. So be prepared to label some areas and use that. So now for the second part, we're asked to do f prime of 14. Well, remember, up here, we've already identified what f prime is. So f prime of 14 is really the same as g of 14. Well, g is the graph. So really all we have to do is follow the graph of g and get to 14, which takes us right here. So at this point right here, the output of that graph is 0. So f prime of 14 is going to be the same as g of 14. That's going to give us an answer of 0. So there's our second answer for this one. And then the last answer we're looking for is f double prime of 14. But again, remember how we set this up in the beginning. F double prime is equal to g prime. So this is going to be g prime of 14. G prime of 14 refers to the slope of this graph. The derivative of g is the slope of this graph. So now we're looking for the slope in this region right here. Well, that's linear. That's why they're telling us we got line segments so we can read the linear graphs. Looking at that, we've got a rise of 1, a run of 1. This is going to be a slope of positive 1. So we know f double prime of 14 is equal to positive 1. The important things to take away from this example, number 1, If you see geometry, use geometry. It's going to be a part of the problem. Number two, if you've got an integral defined function, please make sure you link how the function they give you, in this case g, is related to the function they're asking you about, in this case f. So these three statements become very important. You'll want to make sure you put those all over the paper so the reader knows that you've got them. Let's go ahead and now take a look at part B of this question. In part B of this question, we are asked this time to find the x-coordinates of the critical points of f on the interval from 0 to 15, and then classify them as a relative max, min, or neither. So the first thing we're going to do is we're going to start with critical points. A critical point is anywhere the derivative is equal to 0 or undefined. So since that's a critical point definition, we're going to find out where f, and we're talking about function f here. So where is f prime of x equal to 0? Where is f prime of x undefined? Well, f prime, again, according to our work from before, is equal to g of x. So we're looking for where g of x is 0 or where g of x is undefined. All right. Well, g of x is the graph. The nice thing about this graph is it is continuous. Because it's continuous, we're not going to get any undefined values for g. So we're really just looking for 0 values of g. So we're working on the open interval from 0 to 15. So the first place we see is 0, but we don't need to include that because it's an open interval. So we don't worry about the 0. And now we're just looking to find where are the zeros of this graph. We're going to get one right there at 8. As we continue this graph, we're going to find another one at 14. So what we know right now is that x equals 0 is a critical point and x equals 14 is a critical point. So now we've done the first part. We found the x coordinates. Second part, classify them and then justify. Well, what we know in this problem is that the graph of g is the same as the graph of f prime. So as we look at this problem, what we're seeing is this graph is positive before 8 and it's negative after 8. So what we can say about this is that f prime changes from positive to negative. That means we're going to have a relative maximum. Because anytime your slope changes from positive to negative, you change from your function changes from increasing to decreasing, and that means you have a relative maximum. When we go and we look at 14, what we're going to find out is that f prime changes from negative to positive there. So because f prime changes from negative to positive, we've got a relative min. So for question B, those are the answers we need. That would get us full credit for the exam. We've identified the x coordinates and we've also classified them, okay? Let's move on to part C in this problem. In part C, we're asking about where does f have an inflection point. So what you need to remember about an inflection point. Inflection point, the definition of an inflection point is a point where the second derivative changes sign. So this is going to be a point where, in this case, f double prime of x changes signs. But we're given a graph of g, which again is the graph of f prime. I'm sorry, graph of g is f prime. So we want to know, where does the second derivative change signs? Well, another way to say the second derivative changes signs is to say that f prime changes from increasing to decreasing, or vice versa, decreasing to increasing. So what we're looking for on this now is a place where this graph is going to change direction, basically, where it's going to stop going up and start going down, or vice versa. So as we trace this graph out, it's increasing the entire way until 5, and then it begins its decreasing. That tells us that x equals 5 is going to be an inflection point because we change directions from going up. In other words, the graph is increasing to going down. Okay, so that definitely is going to be an inflection point right here. All right. Now we're looking for where it stops going down and changes at a point to going up. Well, it stops going down here, but it doesn't start increasing. It's flat. So this is not a point where we change from increasing to decreasing. This function does not do that here. And as a matter of fact, it doesn't do it here either because it's 0 the entire way in between. So this is really a sticky point for a lot of students, but you got to remember is because there's not a single point where the graph changes from increasing to decreasing. When I say the graph, I mean the graph of f prime of x. There is no inflection point in this region. So the only place we have an inflection point is at x equals 5. If we want to justify this, you're going to be tempted to say the second derivative changes signs, but we're not given the second derivative. We're given the first derivative. We're given f prime as a graph of g. So the way we want to say this is because, and here we go, we're linking g to f prime because our graph g, which is really f prime, changes from increasing to decreasing at x equals 5. And that's going to be what you need because when you say the derivative changes from increasing to decreasing, you're saying the second derivative changes from positive to negative. And that's a change in signs of f double prime. Okay, so always make your justifications go back to the given information. This is a given information about g, which is really f prime. My justification has to be f prime. That's why you don't see me talking about f double prime changing signs here, because I'm going back to what they gave me. That's how you earn the justification point every time. Okay, so now in the next one, very similar question, but this time they're asking you where is f increasing and where is it also concave down? Okay, so let me see if I can just re-highlight that for us. Where is it increasing and concave down? So you want to take this on by saying, okay, what does increasing mean? What does concave down mean in terms of f? Well, increasing means the function derivative is positive. So we got f double prime, I'm sorry, f prime is positive. So that's what we're looking for. And we're also saying where the second derivative is negative. Okay. But remember, we're talking about g, which is the same as f prime. Notice I'm writing that in every single part of this. So really what we're doing is we're saying, where is g of x greater than 0? Okay. And where is g prime of x less than 0, which means g of x decreasing. So we're looking for any places where g of x is greater than 0. In this case, that means g of x is above the x-axis. So we're looking for where we're above the x-axis and decreasing. So in this whole region, we're above the x-axis. And in this region, we're above the x-axis. So those are potentials. But the second part is you also have to be decreasing. The only place I see that function decreasing is in this region. I just highlighted in yellow. Okay. In this region, we're increasing. The function g is increasing. Same thing over here. So this is the answer we're looking for. Where is this function both increasing and concave down? This guy is going to be increasing on that interval and concave down on that interval. So it seems it starts at 5 and it ends at 8. Okay, so the answer to our question here is 5, and then we're going to go all the way until 8. Now, I personally would want to say that we've got to take a break at 7 just for a second. Okay, so from 5 to 7, but then again, start at 7 and go to 8. And the reason I like that answer instead of just 7 to 8 is because at this point right here, what we know about this is that G prime is actually undefined. The slope there is undefined. That is a cusp, or some of you might call it a corner. It's an abrupt change in slope. Since the G prime is undefined, to me, my way of answering that says it's not less than 0, it's not greater than 0, it's not equal to 0, it's the fourth option, it's undefined. So I feel like we have to have a break there and go from 5 to 7, and then again from 7 to 8. So there's the answer that I would give for this particular problem, okay? But again, the key here is making sure you relate F and G. So I should write a really quick sentence here for my justification. Why am I going to justify this the way I have? Well, I'm going to say this because now I got to talk about F prime here. So why is F increasing? Because F prime of X, which equals G of X, always make the link, is, well, I want to say positive, and I want to say decreasing. because that's how I knew to pick it, because it was above the axis and it was decreasing. So there's my justification for that answer. Let's keep going because there's so many different questions they can ask you with this fundamental theorem. So here we go. We're looking at part E in this one. And in part E, they're asking us to find the absolute maximum of f. Now, this is a problem. Whenever you see these words absolute maximum, what jumps into my head right away is this thing called the candidates test, okay? You want to go and you want to make a candidates test. And the candidates test is all about the following. Candidates test. It's looking at your endpoints and your critical points as the candidates. And once you've identified all the endpoints and critical points, you just see which one gets you the highest or the lowest value. In this case, it's going to be highest. We're looking for the absolute maximum. So what we want to do is we want to identify all the endpoints and all the critical points. So it's very useful in this type of problem to go and make a table, because the idea is you're going to just compare inputs and outputs to find your best value. So we want to find the candidates for f. So the candidates are the endpoints and the critical points. So we're looking for where f prime of x is equal to 0. But remember, f is the same as g. We keep saying that over and over again. So we're saying where is g equal to 0? Those are going to be our critical points. And our endpoints are just going to be given by the problem. We're told our endpoints are 0 and 15. So one candidate is automatically 0. So there's our first candidate, 0. Now our next candidate is going to come where we find a critical point, which means where f prime is 0, which means where this graph is equal to 0. So this is actually a critical point and an endpoint. As we keep moving along the graph, the next critical point we see is right here at 8. So we're going to make 8 a candidate. The next critical point we see comes down is right here at 14. So what I'm going to do is I am just going to copy this table really quickly so you guys don't have to switch back and forth from screen to screen. So the next candidate, we got 8 for that last one. Our next candidate is 14. And our last candidate is going to be 15. It's going to be that endpoint. So here's our job. Our job is to go now and find the outputs for each of these guys. Well, that means using our function f. Well, f of whatever I plug in is equal to the integral from 7 to that value of the input of g of t dt, which means we are going to have ourselves a lot of geometry going on in this problem. We're going to start computing integrals all the way back to 7 and all the way to 15. We're going to be computing integrals up and down this particular function. So what I'm going to do to make my life a lot easier is I am going to break this up into some shapes to start with. And let's just break this up like this. Obviously, we've got a nice triangle before 3. So our first shape I'm going to do is that triangle. Then I'm going to do a cut at 7 to get that shape. Then I'm going to do another one here at 9 because I'm just breaking this up into shapes I can easily identify. Okay, and now I'm just going to go through and I'm going to label these shapes with their appropriate areas as found by using geometry. So that last one I just did, I'm going to cut that semicircle at the top. So here we go. Our first shape is this triangle right here. That's got a base of 3 and a height of 2. That's going to give us a area of base of 3, height of 2, half of 6. That's going to be 3. So that is our region right there. The next shape I see, I'm going to color coordinate here, is this rectangle right here. So I'm going to go and I'm going to compute the area of that rectangle. I could use base times height, or I could also just count the blocks, whatever's easiest. So no matter what you do there, you're going to get an area of 8 for that rectangle. The next thing we're going to look at is that semicircle up there. And that semicircle is half of pi r squared. So I'm going to go and I'm going to compute half of pi r squared for that. And when I do that, when I do that, sorry about that, let me just redo that. Little technical difficulty with my marker. Let's redo that. So when I find that area, it's going to be half of pi r squared. Okay, so that's going to be pi over 2 times the radius squared. Well, the radius here is 2, so that's going to give me 4. So that answer is going to be 2 pi for that shape right there. You may remember from earlier in this problem, we already found the area of that triangle. That triangle is in the area of 1. We also said the area of the triangle below was 1 because those were symmetrical. We also found the area of this rectangle from before. The area of this rectangle we said was 6. And again, doing base times height for that. This last triangle, or not, I shouldn't say the last triangle, but this next triangle, we found that area already. We said that the area of that triangle, let's see here, is going to be half base times height. So half 2 times 2, so that's going to be 4. And then the very last triangle that we've got is this guy all the way at the end, and that's going to be a area of 1/2. I'll just write that over there so we can see it a little better, okay? So I find it much easier just to go through and label everything, because now what I'm going to do is I'm going to start by finding out the outputs for these values, okay? So the first value I'm going to do is I'm going to do 0. So I'm going back to the integral defined function right here. I'm plugging in 0. When I plug in 0, that's like saying I'm starting here at 7, and now I'm going all the way back to 0 in this direction. What that means is all of the areas that are above the x-axis are going to be counted as a negative because they're normally positive, but we're going backwards. So since we're going from right to left, it's the reverse of what we think, which means all of these above the x-axis, they're positive heights, but they're negative bases because we're going to the left. So we're going to get these 3 shapes put together, but it's going to be negative for all of it. So 3 and 8 is going to give me 11. So that's actually going to be negative 11. And then I'm going to have a minus 2 pi. So my output for 0 is negative 11 minus 2 pi. The next one I'm going to do is I'm now going to start at 7 again, but this time my new input is going to be 8. Okay, so I want to know what happens for this point now. So I'm going to plug in 8. So this time I'm starting at 7 and I'm just going to 8. So I'm above the axis and I'm going to the right. Positive and positive means my result is going to be positive, and I'm just going to use the area that's given by that triangle right there. So that's going to be positive 1. Okay, I don't need to write the positive. I'm just stressing that we're going to the right and we're above the axis. So that's positive 1. So now I'm going to do the same thing, but I'm going to do it for 14. Well, this time when I go and I substitute and plug 14 in, I'm going to get f of 14 is the integral from 7 to 14. Now, I've already done some of this work because now I'm still starting at 7, but I'm going all the way to 14. So this time I want to integrate going all the way to 14. That means I'm still going to get this 1 as a positive, but I'm going to get all these as negatives because I'm going to the right, but we're below. So it's going to be positive 1, but then it's going to be minus the rest of those. So when I subtract the 1, the 6, and the 4, that's actually going to be minus, I'm sorry, that's not 4. My mistake. That's not a 4. My mistake. That's not a 4. Let's go back and redo that. That's 2 by 2. So it's half of 4. That's going to be a 2 there. I apologize for that. So now, glad I caught that. So now when I go and I do this, it's going to be a positive 1 here from this triangle, but it's going to be a negative 9 from these 3. So it's going to be positive 1 minus 9. That's going to give us an answer of negative 8. All right. And then for the last one, all I'm going to do is start at the same place, 7, but I'm going to go all the way to 15. So all I'm really doing is just taking this and extending it one more shape. So I'm going to get the same answer I got before. I'm going to get all that negative 8 back, but I've got to add that last shape, which is plus 1/2. Okay, so it's going to be negative 8 plus 1/2. That's going to give me negative 15 halves. So now these were my 4 candidates, 0, 8, 14, and 15. The question is, which is the absolute maximum? Well, I just look and see which one has the highest y value. That value is negative, that value is negative, that value is negative. There we go. There's our absolute maximum. So find the absolute maximum value. The absolute maximum value is, now be careful on this, it's the value. They want the output. We've got to say the absolute maximum value is positive 1. A very common mistake is for students to write x equals 8. That's not the output. That's the input. They want the output. So the absolute maximum value is 1. Now, here is the beauty of the candidates test. When it says justify for the candidates test problem, this is the justification. You don't have to write anything else. This works for your justification. And that's the beauty of it. So you can just write absolute maximum value and you can be done. So my advice to you on this is to label your areas ahead of time, and that way you can just go and literally read the areas off as you're jumping around. Be a little more careful about your areas than I was there. That's an area of 2. And use the candidates test, because therefore, if you do it, you don't have to provide any more written justification. Okay. Let's take a look at the next type of problem they might ask in this super FRQ. All right. So in this next one, they're introducing a brand new function, and this function now is this h of x function. So we look at this and they're saying find h prime of 5. Well, take a derivative. That's all it's saying. So we're going to take the derivative of both sides. This is going to be h prime of x. When I take the derivative of the other side, the 1/3 is a constant, so it's just going to come along for the ride. And now I've got to use the chain rule on this. So the derivative of the outside is f prime of something. Copy that inside, and now take the derivative of that inside to complete the chain rule. And what we end up with is h prime equals 2/3 times f prime of 2x. Now, again, as we've done in every other problem, f prime is really equal to g. So that's going to tell us we've got 2/3 of g of 2x. When we go to do h prime of 5, that's saying to substitute in 5 for x, so that's 2/3 g, and this is going to be 2 times 5 from down here, so it's actually going to be g of 10. So now, final answer, we're getting really close. All we've got to do is find out what g of 10 is. Well, g of 10 can be read from this graph. So there's g of 8, g9, g of 10. So g of 10 is right there. That is the input 10 and the output -2. So we're going to put a -2 in for this. And that tells us that h prime of 5 is going to equal -4/3. -4/3. Okay, so that's what we're looking for here. So again, it's going back to the graph every single time, but we're still using our calculus. Don't forget about your chain rules, or you're always want to be on the lookout for using the chain rule. So the next example actually takes this function, this 1/3 f of 2x, and asks another question. Okay, so let's just remember that h of x equals 1/3 f of 2x. And now in this one, they're asking us to find the equation of the line that is tangent to h at x equals 7. My students have been programmed to always start this by writing down the point slope form of the equation. They know they're looking for 3 blanks. We're looking for an x value here. We're looking for the, and usually it's called x equals a. We're looking for the output when we plug in a for that one. We're looking for the derivative when we plug in a for that one. But in this example, be careful, because we're not finding the equation of the tangent line to f, we're finding it to h. So let's go back and let's be really specific about this. Let's say we're finding h of, well, our a value in this case is 7. So let's do this the right way. It's going to be 7 for that value, h of 7 for this value, h prime of 7 for that value. So in goes the 7, and now I'm finding h of 7 and h prime of 7. Well, h of 7 is given by our function up here. It's 1/3 of f of 14. Okay, that's going to be h of 7, 1/3 f of 14. Well, to find f of 14, that would mean going back to this guy and saying f of 14 is equal to the integral from 7 to 14 of g of t dt. Well, if we're doing the integral from 7 to 14, again, we kind of have already done this a couple of times. We know that this value here was 1, and this value here was 1. We know that going to 12 gave us 6 more, and we know that going to 14 was half base times height, half of 2 times 2, which is 2. So as we go and do this integral from 7 to 14, we're going to be moving left to right. So the 1's going to be positive, the other one's going to be negative, the 6 is going to be negative, and the 2 is going to be negative. So when we work that all out, we're going to get -8 for this example here, okay? We're going to get -8 for f of 14, but remember, it's 1/3 times that answer. So that's -8/3. So there's our h of 7. It's going to be -8/3. So we're going to put 8/3 in that blank, and we're going to make that a negative, which makes it positive. So now the last thing to do in this problem is find h prime of 7. But remember what h prime was. Let's go back up here. Let's recompute that. That's going to be h prime of x is equal to, it was 1/3, and then the chain rule went into effect. So it was f prime of 2x all times 2. That was 2/3 f prime of 2x. So h prime of 7 is going to be 2/3 f prime of 2 times 7, which is 14. Well, when you go to find f prime, remember, this is the graph of g, okay? And g is equal to f prime. So I'm looking for f prime of 14. Read it from the graph. We're talking about this value right here. So f prime of 14 is equal to 0. So that actually means we've got a 0 slope or a horizontal line. I would tell my students just to leave this problem exactly the way it is. This is perfectly acceptable. A lot of people will want to say that this side goes to 0, so we've got y by itself being y equals -8/3. Of course, that's an acceptable answer, but you don't get extra credit for that, so I would just leave it right like this, okay? So let's go now and take a look at the very last part of this free response question. We're finally getting to the end. So in this one, you are asked, that tangent line we just computed, if we use it to approximate h of 2.1, would the result be an over approximation or an under approximation? Okay, well, tangent lines and approximations, what you got to remember is that if you have a function, let's just draw this down here out of the way. If you have a function that looks like this, okay, and you have a tangent line approximation to it, what that's going to mean is you're touching at that one value. So this would be touching just like this, okay? So this is our tangent line approximation. Well, the red values are the approximate values, and the blue values are the actual values. Well, in this case, the approximate values are always less than the actual values, because they're beneath it. They're underneath. The only place they're not underneath is at the point of tangency. That's the one place they're the same. So for a shape like this, the approximate is less than the actual. How would we get it to work the other way around? The shape would have to look like this. If you have a shape that looks like this guy, and now you draw your tangent line wherever you want it. Well, in this case, the red are the approximate, and the blue are the actual. And in this case, the approximate are greater than the actual. I hope by looking at this, you're starting to see what's going to cause this to happen. It comes down to the concavity. If you're concave up, your approximate values are less than your actual values because your tangent line will be below. If you're concave down, your approximate values will be greater than your actual values because your tangent line is above and your shape is below. So if you're asked to ever find out whether or not a tangent line approximation is an over or an under approximation, that is code for find the second derivative and check the concavity of the function. So what we want to do here is we want to find the concavity of h. So we know h of x is equal to what do we say it was equal to? It was equal to that function 1/3 f of 2x. We've also seen that h prime was equal to 2/3 f prime of 2x. Well, we got to go one step further. We got to do h double prime of x, and that's going to be equal to 2/3. This time it's going to be the second derivative of that inside function times the derivative of that inside function. So h double prime of x is equal to 4/3 f double prime of 2x. And the question is, what is the concavity at and around x equals 2.1? So the concavity here, that's going to be looking at the concavity really kind of like this, h double prime of 2.1 That's 4/3 f double prime of 2 times 2.1, which is about 4.2. So we're looking around x equals 4 in the graph of f to find out what's going on. Well, remember, the graph of g is really f prime. So f double prime is the slope of g. Well, when we look around 4, what we're talking about is looking around this region right here. Well, although I can't compute it directly, I do see that that slope is going to be positive everywhere in that region. So what we know is that h double prime is going to be, h double prime of 2 is going to be greater than 0, which means that h is concave up in this region. And if h is concave up, that means the tangent line approximation, well, remember, if you're concave up, you're below, so the tangent line approximation is going to be an under approximation. This particular example takes you through all the different questions that I've seen over the last 20 years or so that talk about using the fundamental theorem of calculus in conjunction with an integral defined function and using geometry to get the answers. I hope this really makes a lot of sense to you guys. Personally, I'm telling my students I'm quite confident they're going to see a problem like this, so I hope you get one tomorrow and that you guys are able to crush it, okay?
Let's take a look at this one together. Okay, so separable differential equation question. Here we are first asked in part A to just provide a slope field, okay? Draw the slope field. So when we look at this one, the slope field is really just as simple as plugging in each of those values into our derivative. Okay, plugging each of these values into our derivative. So what I happen to notice about this one is we've got an x squared minus 1, which means anytime we can square x and get 1, this slope is just going to turn into 0. So what that means is we're basically going to get a lot of 0 slopes in this because everywhere x is 1 will have a 0 slope. So that means all along the x equals 1 line, we're going to see 0 slopes. But we're also going to have 0 slopes along the x equals negative 1 line. So we're going to have 0 slopes in all of those places as well. Okay, then if y is equal to 0, we're also going to have a 0 slope. So that means we're going to have a 0 slope where y is 0. That's going to be at the origin. So now what we really need to do is we really just need to evaluate this slope in 2 places. We need to evaluate at the point 0, 1. Okay, so when we plug in 0, 1, our derivative at 0, 1 ends up being 1 times 0 minus 1. And that just ends up being negative 1. So what you're going to want to do is you're going to want to try to draw that slope as close to 45 degrees as possible, okay? Because they're going to be looking at these slopes, and they're going to be looking for your horizontal slopes to be flat, and that's what we saw in each of these cases. They're going to be looking for your slopes of I just drew a slope of 1 there. That should actually, let me double check that. That should be a slope of, that should be a slope of negative 1. I apologize. I've got a slope of 1 there. So that should be a slope of negative 1. They're going to be looking for your slopes of 1 and negative 1 to be negative, okay, and be about 45 degrees. And now we're going to go and we're going to do dy over dx, and we're going to evaluate this at the point 0, 2. Okay, so when we evaluate this at 0, 2, what we're going to get is we're going to get 2 times 0 minus 1, and that's going to give us negative 2. Now, you don't have to be perfect about this, but you do have to be consistent. So your slope of negative 2 needs to be steeper than your slope of negative 1, okay? And if you just want to make sure, it probably wouldn't hurt just to write slope equals negative 1 there, slope equals negative 2. It couldn't hurt just to be clear, just to make sure. So the slope field question is a pretty common question, and you just go through, you draw your slopes, and you make sure that they are in the right place. So for the next part, and this is the one that's really kind of the big ticket, the next one is the big ticket one. It's this one here. We're going to jump to part C. Okay, and in part C, what you need to do is you need to solve the separable differential equation. So, very, very, very common question.
And it's solved the same way pretty much every single time. So let me just take you through this to make sure that you're ready for it, okay? When you see the separable differential equation question, what it really means is that you're going to separate the x's and the y's. So you're going to want all the x's on one side, you're going to want all the y's on the other. And the way you're going to do it is you're always going to take advantage of multiplication. So you're going to want to multiply to get all the y's on one side, all the x's on the other. So what we're going to want to do is we're going to want to keep the differentials in the numerator. So the first thing we're going to do here is we're going to take this dx and we're going to multiply it over the other side. So when I multiply that dx over to the other side, it's going to get rid of the dx here and it's going to bring it over there. So that is going to put a dx up in the top. Now you've got almost all x's on this side, but you also have a factor of y. So what you've got to do is you've got to move that factor of y to the other side. So you are going to multiply both sides by 1 over y. So I'm now going to have 1 over y dy equals x squared minus 1 dx. Okay. Once you're here, and it's important that I like to write it as 1 over y, because the next step, once you've got the y's on one side and the x's on the other, your next step is you're going to integrate both sides. So here we go. We're going to do the integral of the left side. We're going to do the integral of the right side. So if you're trying to score this one, you automatically get 1 point just for separating your x's and y's. So again, before I did that integral, that earns you your first point. Now you're going after your next points, and your next points are going to be to find these antiderivatives, okay? So you're going to try to integrate both sides. When you integrate the 1 over y dy, you're going to end up with the natural log of the absolute value of y. And then on the other side, you're going to integrate term by term, so you're going to get x cubed over 3 minus x. And now you've got to remember that constant. Okay, where is that constant going to end up? Well, technically there's a constant on both sides, but you can always just move them to the same side. So what we tend to do is just put the plus c over on the x side only, okay? So once you're here, you're in pretty good shape. The only thing you have left to do now is to solve this for y and find the value of c, okay? So they've given us a condition. The condition is up here. It's f of 0 equals -2. We could go and we could actually find the c now, or we could find it later. I always find it at the end. That's my preference. If you find it now, that's perfectly okay. Both ways are perfectly acceptable. I'm going to go and I'm going to continue to solve this for y. So what I need to do now is I need to get rid of the natural log on both sides. So the way we get rid of the natural log is we raise both sides as exponents, and then we use the base of e. Okay, so by doing that, we're going to take our equation, basically put it up in the exponent. But what's going to happen that's really nice is when you've got an e acting on an ln, those guys are going to cancel. So we're now going to be left with the absolute value of y is equal to, and this is going to be kind of interesting on this side. I'm going to work with it a little bit over here, because this is one of the College Board's favorite simplifications. We see them use this a lot in the multiple choice. We see them use it in the free response. Again, the free response is not that important because you don't have to simplify, but they love to use this in the multiple choice as well. So I just want to take you through it. It's built on the idea that when you add exponents, you're really multiplying like bases. So what's happening is I've got this exponent being added, which means it's the same as multiplying e to the c there, okay? Because if I were going to multiply these two e's together, that's really adding these exponents. So that would get me here. Now, why do they make such a big deal of this? Well, it's because that e to the c is a constant. So you can actually rewrite this as, you know, a new constant. Oops, sorry about that. A new constant times e to the x cubed over 3 all minus x. And the College Board uses that simplification a lot. So I want to point that out to you, okay? So what we're just saying is that, you know, this e to the c right here becomes that c right there, okay? It's an arbitrary constant, so we haven't solved for it yet. It can just be written as c. So that gives us that the absolute value of y equals ce to the x cubed over 3 minus x. So at this point in time, you've got these absolute value bars over here. Now, a lot of us are just going to say, well, can't we just get rid of them? Can't we just drop them? But the fact of the matter is, we don't get to decide. The condition decides, okay? So we're told that the y value here is 2. If I use 2 in for y, if I put a 2 in right here, the absolute value bars don't do anything. I can rewrite this as just plain old y equals ce to the x cubed over 3 minus x. Okay. Had that been a negative 2, had this guy been a negative 2 over here, then the absolute value bars would have to change it to a positive value. I would have written this as negative y. All right. But because I was using a positive 2, that meant the absolute value bars weren't necessary. So I get to use just plain old y. That's how I handle the absolute value bars, by using the condition. Okay. So if the y value makes your condition positive, you don't need a negative in front. If the y value makes your condition negative, makes your absolute value negative, then you will need it. So from here, we're just going to wrap up. We're going to plug in 0. We're going to get out 2. So what that says is that if I get out 2 when I plug in 0, I'm going to get 0 cubed over 3 minus 0. Basically, it's going to turn to 2 equals c e to the 0. Well, e to the 0 is 1. So we're just going to get that c equals 2. So we come back up here, and we're ready to give our final answer. Y is equal to 2e raised to the x cubed over 3 minus x. And that is the final answer that we're looking for the separable differential equation question. Okay, so let me just take you through this again, because the chances are very high you'll probably see a problem like this tomorrow. I just want to make you aware of this. You get a point for separating the y's and the x's. You get a point for finding the antiderivative of the left and the antiderivative of the right. So that earned points right here. That's 3 points total. You're now going to get a point for evaluating the constant and getting the right value for the constant. And we got c equals 2. And your last point is going to come from giving your final answer. Okay, this is asking for the particular solution. Particular always means we use our condition, and that's going to be worth 5 points if you see it on the exam tomorrow. So hopefully you'll be ready for that should it show up. At this point in time, we're down to just a little over a half hour left. What I want to do is turn our attention now to just some last minute vocabulary. You guys have been working so hard that at this point in time, I just want to make sure that everything is fresh in your mind for tomorrow. So we're going to go and we're going to switch this back to the PowerPoint, and we're going to talk about our last minute reminders. Okay, so if you guys are ready, we're going to go through and take a look at all of this. So here we go. Okay. So again, a trip through the vocabulary of AP Calc exam and some of the most common errors and mistakes. So there's going to be a lot of information thrown at you here, and it's all meant just to remind you of all the things that could possibly happen tomorrow. Okay, so we're going to start kind of do a course review in terms of vocabulary. So the first one we're going to talk about is discontinuities. Okay, when we're talking about discontinuities, there are removable discontinuities. Now, I always call the removable discontinuity a hole. So when you look at this particular graph, you see two different types of discontinuities. You see one at 2 and you see one at 6. The one at 6 is the removable discontinuity. The way I know that is because for a removable discontinuity, the limit will exist. So when we look at this problem and take the limit at 6, we don't get -3. I apologize. We get the limit is -1. That is an error there. The limit is -1. So there is a hole there, and that is a removable discontinuity. So that is how you know you've got a hole, and that is going to be a removable discontinuity every single time. Along with that, continued on the discontinuities, there is the jump discontinuity. Now, this one here is the jump discontinuity, because you can see that the y value jumps from one branch of our function to the other. There is no limit that exists here, because as we come from the left, the limit is -1, and as we come from the right, the limit is 0. So anytime you come from the left and the right and you get a different answer, that's going to give you a jump discontinuity. The last type of discontinuity you need to be familiar with is the vertical asymptote. And in the case of the vertical asymptote, when you come from the left and you come from the right, what that means, you're going to get an infinite result. Okay, so if that happens, if you get the infinite result, you've got a vertical asymptote. So if they should ask you, and this has been common in the multiple choice the last 4 or 5 years, about any of these 3 different types of discontinuities, that is what you need to know. Our next term is differentiable. I know you worked with this with Megan a little bit earlier, so we're just going to make sure it's clear. Differentiable. In this graph, you've got a couple of places that are not differentiable. But to be differentiable, what that means, first of all, you are continuous. So what you see right there, that's your definition of continuity, with the limit from the left equals the limit from the right equals the function itself. You can't be differentiable unless you are continuous first.
But there's more, okay? Once you know you're continuous, you then have to make sure that the limit of the slopes agree from both sides. So in this particular one, right here, we're going to find that the slope is going to have a little bit of a disagreement because coming from the left and coming from the right, we have this sharp change right there. So let's take a look as we go through this. That value right there is not differentiable for the reason I just said. The slope from the left does not agree with the slope from the right. We call that a cusp or a corner. And you'll see another one of those in this graph as well. One right there at 2. This is also not differentiable for the same reason. The slope from the left does not agree with the slope from the right. That is not differentiable either. And there is a third place we're not differentiable. This one's a little sneakier, okay? This one's not differentiable because we actually have a vertical tangent line right there. And if you have a vertical tangent line, that means that your derivative is undefined. So those are the two ways you can be continuous but not be differentiable. Sharp changes in slope called corners or cusps, or vertical tangent lines. This is something that I always show with my class. It's a little graphic organizer called the pyramid of differentiability. And the pyramid of differentiability works in the following way. There are layers to it. Okay, so this is how it works. What you know, sorry about that. What you know is that if you are a function, every function has a domain. So everyone has this bottom level. But as you work up the pyramid, not every function is going to have limits that agree. So we're going to lose some functions. So you don't automatically get to have a limit just because you have a domain. But if you do have a limit, you will have a domain. It works the other way. Then to get to the next level, you've got to get to continuity. That means if you're continuous, your limits must agree. So if you're on the top, you have everything that goes below it. And then finally, the very, very top of this is differentiability, okay? If you're differentiable, it means you've got the continuity, it means you've got the limits, it means you've got the domain, you've got everything underneath it. So if they ever start off by saying that you are a differentiable function, you automatically know that you're continuous and that your limits exist. All right, so there we go. The next vocabulary I wanted to stress with you guys to make sure you're ready for it. The critical points and inflection points, they sound very similar, but there's a slight nuance to them, okay? So a critical point is a point where your first derivative is either 0 or undefined, okay? That's it. So again, it has to be a point. So the function has to have a value there. But as long as you have a value and your first derivative is 0 or undefined, you are a critical point, okay? You can classify critical points. And very often they ask you to classify critical points. And the way you classify critical points is either as a relative maximum or a relative minimum. For a relative maximum, you must see a sign change. Your first derivative has to change signs from positive to negative. For a relative minimum, again, got to be a sign change. You got to have your first derivative changing from negative to positive. Notice the critical point does not require a sign change. Critical points just need a derivative to be 0 or undefined. The max and the mins require the sign changes. When we go to inflection point, this is one of the most common mistakes every year at the reading. An inflection point is all about where the concavity changes. So we're talking about the second derivative now. And for an inflection point, your second derivative must be 0 undefined. But there's more. You have to have the sign change as well. So the inflection point is actually like the critical point and the max and mins get smushed together in the same thing, but only for the second derivative, because you need both the 0 and the sign change to be an inflection point. Never call something an inflection point if you can't show that the second derivative changes signs. Okay, you've got to have a sign change. If you come across a problem that asks you for an absolute max or min, we saw one of these earlier. You want to use a candidates test. You want to compare the outputs of all the critical points and the endpoints. And by doing that in the table form, and here's the example we saw earlier, doing that in table form, you can just pick out the absolute maximum value right away. You don't have to write anything. You don't have to justify it. The table will justify it for you. The next thing we want to make sure you're clear on is the definition of the derivative. There are a lot of problems that use the limit definition of the derivative in the multiple choice, okay? And one thing I just want to remind you, here's our limit definition of the derivative. But when you see this, notice this is equal to f prime of x. Well, that's just another way of saying it's equal to the derivative of this piece right here. So if you ever see something in this format, they're asking you about a derivative. But here's the good news. Even if you're not quite ready to use the limit definition, you can always use L'Hopital's rule to do these limits. L'Hopital's rule will always apply, so you can knock out these limits by using L'Hopital's rule instead. And speaking of L'Hopital's rule, We've seen this a couple times tonight. L'Hopital's rule is when you're taking the limit and it results in an indeterminate form. That means you're going to get 0 over 0 or infinity over infinity. In free response, I said it earlier during my first session tonight, never write that the limit is equal to these indeterminate forms. It's not correct mathematics to say you're equal to an indeterminate form. If you're going to show L'Hopital's rule, you've got to show that, first of all, that you get the limit of the numerator to be 0 and the limit of the denominator to be 0 separately. If you can show them separately, that's enough to use L'Hopital's rule, and that will be able to justify your work on the free response section. Here's something that I don't know if we've talked about too much tonight, and it's estimating. Now, there's always a question every year about estimating, and the 3 types of estimates that you can be asked for on the AP exam are the following, okay? You could be asked to estimate a derivative, you could be asked to estimate an integral, or you could be asked to estimate a function. Now, depending on which of the 3 that you are asked, there is a set way to do each of these. If you're asked to estimate a derivative, you're always going to use an average rate of change, which is a 2-point slope. Okay, just use the 2 points closest, find the delta y over delta x, and then that's going to get you credit for the estimation for the derivative. And there is the mathematical notation that goes with that: f of b minus f of a over b minus a. If you're asked to estimate an integral, you're going to use a Riemann sum. And the Riemann sums that you're familiar with, or should be familiar with, are left Riemann sums, right Riemann sums, trapezoidal, and midpoint. And we're going to talk about each of those briefly as we continue this whirlwind review here at the end tonight. Okay? And then if you're asked to estimate a function, you're going to use a tangent line to estimate that. And again, I know Megan had done some work with you guys on that already. You're going to set up in this form where you're going to solve it for y, and it's going to equal the y value at the point of tangency plus the derivative at the point of tangency times the x minus the x value of the point of tangency. And that's going to be how you estimate a function. So anytime you're asked to estimate, these are the 3 things that you're going to be looking for. We did some work with theorems this evening. I know Megan worked with you earlier. I just want to remind you guys, always state that the conditions are satisfied. If you're going to use the extreme value theorem or the intermediate value theorem, you must say that you have a continuous function on your intervals first. Write it down, put it in the answer, say that the function is continuous, and then show that it's continuous on that interval. Okay? If you're being asked to use the mean value theorem, you think you have to use the mean value theorem, the first thing you should write down in your problem and the free response is say, since the function is differentiable, which is usually given in the stem. So you'll say, since the function is differentiable, therefore the function is continuous, and then go and actually show the mean value theorem, show the 2-point slope equaling that instantaneous rate of change. And then the last one that you've got to set up is L'Hopital's rule. We've talked about this numerous times. Show that the top goes to 0 and the bottom goes to 0 as 2 separate limits. Same thing if it's infinity, okay? Always as 2 separate limits. And there's the 2-point slope that you need to show for the mean value theorem as you're using it, okay? This next one, kind of an interesting question, the integral versus area. So many of us think that integral and area are the exact same thing. You've got to be really, really careful when you're talking about integrals and areas on the exam. And I'm going to show you where they come up. So here is a function. This is actually the graph of sine between 0 and 2 pi. If we asked you to integrate this function, okay, this function from 0 to 2 pi, you're actually going to get the answer 0. And that's perfectly okay, because the integral does not force it to be positive. The integral allows there to be negative area. So when you look at this, that bump right there, if you work that out, that actually has an area of 2, okay? Well, the bump below is symmetric. It also has an area of 2. But when you integrate this, the integral will treat this bump as a positive 2, but it will treat this bump as a negative 2. So as the integral adds from 0 to 2 pi, you're going to get 2 for the first bump, negative 2 for the second bump. That integral is going to give you an answer of 0. Okay, and that's exactly what you want. That's what the integral does. However, if you were asked to find the area, you've got to make sure that everything is positive. And the way you're going to do that is you're going to break this into 2 separate integrals. You're going to have to integrate the first one, and you're going to do the function minus the axis to make sure that that's positive for the integrand, and that's going to be from 0 to pi. And then you're going to do the same thing in the second bump, but you're going to do the 0 minus your function. And when you set it up this way, you're guaranteeing that the function always has a positive value. That means your first bump will give an answer of 2, and your second bump will also give an answer of positive 2. So you'll get that answer of 4. A shortcut for doing this is to make use of absolute value. If you just put absolute value around the function, what's going to happen is that second bump will flip above the x-axis, and you're automatically going to get a positive answer. Where else is this important? Well, same exact graph, different question. What if this was a velocity function this time and you're asked for displacement? Well, displacement is the equivalent of the integral. Displacement is allowed to have those negative values. So when you find the displacement on this one, you want that to be 2, and you want this one to be negative 2, because you want the displacement to be 0. That bump above the axis really says because the velocity is positive, we're moving to the right, and then the bump below says the velocity is negative, so we're moving to the left. So the amount we go right cancels with the amount that we go left. That gives us a displacement of 0. However, the other question that you can get asked is to find the total distance traveled. In this case, you don't want the right distance canceling with the left distance. So this is an area problem. The exact same thing we did before. We're going to set this up so that everything stays positive. Or again, if you want to make it easier, you put absolute value on the velocity, and it's bound to stay positive that way. Okay, so that's area versus integral, and the most common application is distance and displacement. All right, we're going to now look, and we're going to go through all the different Riemann sums, because a very popular question over the last couple of years has been, are these overestimates or underestimates? So as we look through these, if you've got a right Riemann sum on an increasing function, if you draw the picture, it actually makes a lot of sense. You can see that this is going to be an over approximation. Okay. If you've got a right Riemann sum done on a decreasing function, this is always going to give you an under approximation. If you've got a left Riemann sum with an increasing function, this will also be an under approximation. And if you've got a left Riemann sum done with a decreasing function, you're going to get an over approximation. If we now look at midpoint, and last year was the first year in my recollection that they actually asked about midpoint and whether or not it was an over or under approximation. So a lot of students struggled with this last year, but hopefully you'll be all set, because if you're doing a midpoint Riemann sum, this time it's not about increasing and decreasing. This time it's about concavity. So if you're doing a midpoint Riemann sum and your function is concave up, you're going to have an under approximation in this situation. Okay, so again, kind of a newish question. We haven't seen a lot of these over the years, but they did ask it last year. Okay, if you've got a midpoint Riemann sum and you're doing it with a concave down function, this is going to be an over approximation. The last one for Riemann sums is the trapezoidal rule. And again, this doesn't depend on increasing or decreasing. This depends strictly on concavity as well as the midpoint. In this case, the trapezoidal Riemann sum is with a concave up function is going to be an over approximation. You can see that it goes over the curve. And then the trapezoidal Riemann sum done with the concave down function is going to be an under approximate. Trapezoidal with the concave down function, this is actually going to be an under approximation. Okay, I think I said over there, that should be an under approximation. All right, so those are the Riemann sums. And just remember, the trapezoidal rule works the reverse of the midpoint. Okay, again, if you're a trapezoidal and you're concave up, that's going to be an over approximation. If you're a midpoint with a concave up, it's going to be an under approximation. So now with our last 20 minutes, for you guys who've stuck it out the entire 5 hours, I can't tell you how grateful I am for staying with me through the technical difficulties we had. I hope this is going to be a good last 20 minutes to get your mind squared away and get ready for that exam. We're just going to talk now about some test-taking strategies. So here we go. The first one, don't leave any of your multiple choice questions blank. You don't get any points deducted for getting them wrong. Leaving them blank does nothing for you. So make sure that you don't leave anything blank at all. If you can narrow it down, eliminate a few answers, your chances will go up. So again, don't leave anything blank. Here's one that is an interesting one. Bubble as you go. And the reason I say that, I had a student 1 year who actually did all of their work in the test booklet and didn't bubble anything until the end. They waited to the last 5 minutes. They thought they could get through it faster. So they waited to the last 5 minutes, and then they went back and they bubbled everything. They actually ran out of time and ended up leaving 10 questions blank. Okay, so bubble as you go and just take your time. Make sure you bubble the right letter. A lot of careless mistakes are made from students bubbling the incorrect letter. Okay, so bubble as you go on that multiple choice. This next one is one of my favorite quotes from the former UCLA basketball coach John Wooden from the 60s and the 70s. Be quick, but don't hurry. What I mean by that, what he meant by that is you're going through the test, you're very deliberate, you're moving quickly, but don't rush. Don't go so fast that you're hurrying. Hurrying leads to careless mistakes. Slowing down, taking an extra 5 or 10 seconds to make sure you're not making any careless errors to get one problem right is well worth it, okay? So go through everything very quickly, but don't go so fast you're hurrying and making careless errors. The next one I alluded to a minute ago, make sure you bubble the correct letter. Go through the work, find that answer, and make sure that you put it in the right spot and you bubble the correct letter. As you guys all know, there is a calculator section and a non-calculator section on the multiple choice test. When you are doing the calculator section, you guys are going to see 15 questions in that calculator section. About 6 of them are going to require the use of a calculator, okay? Just because it's in the calculator section doesn't mean it requires the use of a calculator. You're only going to need your calculator for about 6 of those 15 questions. Make sure that on the ones that don't require a calculator, you're not trying to use it, because all it's going to do is slow you down. Of those 15, again, 6 are going to be calculator, roughly 6 or 7. 6 of them, the calculator is not going to help you at all. There's not going to be any numbers in them at all, so you're just going to have to read it and answer them. And then the remaining questions are going to be what we call calculator neutral. If you want to use a calculator, you can, but a lot of you will be able to do the calculations just as quickly without, okay? So don't be surprised if about half or a little more than half of the calculator questions don't require a calculator at all. And again, this is multiple choice we're talking about. Those first 20 questions, if you were with me for the first hour this evening, this is what I was trying to prep you for. There are going to be so many skills questions in those first 20 questions, just straightforward derivatives, integrals, and limits. Be ready for them and just crush those. You know, you want to make sure you get those right. Those are the most straightforward questions. In some ways, those might be the easiest questions on the multiple choice section. So be prepared for those and just be in your highest level of concentration. Make sure you can get those. If you're stuck on a problem, read the question again. Everything you need is going to be in the question. If you're stuck, you might be missing something that you just read too quickly. Go back, reread the question again, find the thing you're missing. We're now going to shift over. We're going to talk about some free response test-taking strategies, okay? If you make a mistake, don't bother erasing it. Just cross it out with one line. And that's only if you have a better answer. If you cross it out to leave it blank, you're guaranteed nothing. I've gone to the reading. I've seen kids cross out work, leave it blank, and we can tell that if they just left it not crossed out, they might have earned some partial credit. So if you have a better answer, you cross it out with one line. If you don't have a better answer, don't leave it blank. Just leave the work you've got written there. You might be able to earn some points for it, okay, some partial credit. In that free response question, I call it a 2-4 split. Okay, what that means is the first 2 questions, the first 30 minutes of free response is a calculator active section. You'll be able to use your calculator as much as you want on those first 2 questions for those 30 minutes. When the 30 minutes is over, you have to put your calculator away, but you don't put away the questions. You get to keep the 2 questions out. So you just have to put the calculator away. And then a new timer starts with 60 minutes and you get 4 brand new questions. So for the last 60 minutes, you actually have all 6 questions out on your desk. You just don't have the use of your calculator. Just like in the multiple choice, not all the questions in the calculator section require a calculator. When getting a decimal final answer, you have to round or truncate your final answer to 3 decimal places. Again, only your final answers. You don't want to round in the middle of a problem. If you start rounding too early, you might round yourself out of a right answer. So again, final answers get rounded, intermediate answers do not, and you have to have 3 decimal places. Because you don't want to round an intermediate, use your calculator to store your complete decimal values. Okay, store them as a letter, and then you can use that on your calculator. And that way, you don't have to type in the long decimal. It's really easy to transpose 2 digits. So store them, and then you'll have them ready by recalling them on your calculator. On the exam, you can name your functions and the decimals. In other words, if you come up with an answer where you find a point of intersection when you're graphing and you're integrating, and it's equal to 1.2345. You can write let capital A equal 1.2345, and for the rest of your work, you can just write A instead of that decimal. It's a time saver. It really helps. So if you're coming up with a decimal, this is really popular in the area problems. Find the intersection point and then give it a name like A or B, and then just call it A or B everywhere else on the question. As long as you make it clear to the reader that you named that value A, you can call it A for the rest of the way. When writing justifications, do not use pronouns. Readers are instructed that if you use pronouns, you get it wrong. So don't say it is increasing because it is positive. Say the function f of x is increasing because the derivative f prime of x is positive, okay? Pronouns are an automatic way to lose your justification point. Speaking of justification, when you're justifying something, you can use a written statement, but you can include mathematics as well. Mathematical notation is language. You can be a hybrid of part English, part mathematical notation. It's all good as long as it's clear. On the free response section, avoid abbreviations other than for the theorems. The readers are told that the theorems can be used, so IVT, EVT, MVT, FTC. Intermediate value theorem, you can write the abbreviation. Same thing with extreme value theorem, mean value theorem, fundamental theorem of calculus. But avoid abbreviations anywhere else, okay? You're there, it's the one day. Be clear, be concise, be articulate. Make sure you're communicating to the readers. The next one, units. If a problem gives you units, you need to use them, okay? Don't ignore the units. Setting up the units can lead you through the problems. I know Megan worked with you guys in the rate in, rate out problems. To me, the units are the key to getting those right. A lot of times, same thing is true in the particle motion problem. So really, really pay attention to your units. You saw me making use of sign charts and number lines this evening. Sign charts, number lines, they are allowed on the exam, but they won't be graded. So don't think that that will satisfy as your justification. The justification really needs to be a written statement, okay, a written sentence. So don't just leave it up to a sign chart or a number line. Make sure you answer the question. There are a lot of problems where they ask you for the absolute maximum value of a function, something like that. Make sure you give the y value and not the x value. You know, always just take a second to read the question and read your answer before you move on to make sure you're answering exactly what is asked of you. Try all the parts of the free response questions, okay? In other words, if you're having trouble with part A, that doesn't mean you're shut out of part B, C, and D, okay? If you're having trouble with part A, you're still going to be able to earn points on part B, C, and D. They don't always build that way. So, you know, if you're having trouble with an earlier piece, don't skip the rest. Read it, fight for your points. Every point's going to count on this exam for you guys. Okay, we're going to talk about that in a little bit. But you want to make sure you can scrape up as many points as you can. So again, nothing blank. Don't skip anything. Excuse me. You've probably heard this before. You don't have to simplify any of your answers on the free response sections, okay? 5 plus 7 is an answer that's just as acceptable as 12, okay? If your final answer says the sign of pi over 2, you don't have to write it as 1. You can leave it the sign of pi over 2. No arithmetic simplifying is necessary. In the free response section, a lot of questions say round to the nearest whole number. Pay attention. Please don't give a decimal answer on those. Again, at the reading, we see that every year, kids who don't read the directions and give a decimal answer when the prompt says round to the nearest whole number. Make sure if it says round to the nearest whole number, you're not losing points because of that carelessness, okay? Same is true for the setup but do not integrate prompt. There's a lot of those area volume problems where you just have to set up an integral. That's your final answer. They don't actually ask you to integrate it, okay? So again, careful attention to the questions and what they're asking. On the calculator section, there are the following things that you are allowed to use your calculator for, and you don't have to show your steps. So the first one, when you're solving an equation, write the equation down and then go directly to the answer. That's what you're allowed to do on that free response if you're using your calculator. So you can solve an equation, but you must have the equation written on your paper, and then you must have the answer. You can take the derivative at a point. So if they say evaluate f prime of 7, you can just write f prime of 7 equals and then the answer, okay? You can do it on your calculator. You're not responsible for showing your work. A definite integral. You have to show the integral. You have to write the integral from 1 to 7 or whatever it is of f of x dx, but then you can just write the answer, okay? You don't have to show your work for that. And then, of course, you can use your calculator to graph any function and do any calculations at all. And again, you don't have to show your work. Some general exam strategies coming up now, okay? So we're talking about the exam itself, so some general exam strategies here. Okay. Okay, on this one, okay, let me explain what this is all about. The exam. If you earn 40% of the points available, that's approximately a 3. You're going to walk away with a 3 if you can come up with 40% of the points. Okay. If you can get 50% of the points, 50% of the points is going to get you approximately a 4. And then if you can come up with 67% of the points, that's going to get you a 5. Now, let's put that in perspective. Okay, let's just take a look at this really quickly here. Let me get my iPad up and run it again so I can share this with you. When you think about the exam itself, there are 108 points available for you on the exam. Okay, 108 points. So when you think about that, okay, you're talking about how many points you need. 108 points. What we're saying is if you score around a 70 or more, that's going to get you in that 5 range. Okay. When you're looking at the 4 range, we're talking about 50% of the points. We're talking about 54 points out of the 108. That's going to get you a 4. And when we're talking about a 3, a qualifying score of 3, we're looking for about 40% of the points. We're talking about a 42, 43. And again, these aren't fixed in stone, but they're always very similar to these values, okay? So these are the values that are roughly the cut scores. 42 points out of 108 is going to get you guys credit. You guys can do this. You can come up with 42 points on tomorrow's exam, okay? 70 points is going to get you a 5. You know, that's it. So if you're thinking about this in terms of, you know, your college credit, what you're looking for is, again, the idea is you're trying to earn somewhere in that neighborhood of 40 points on tomorrow's exam. 4 out of every 10 points. You want to pick up those points, and that's going to get you credit. So the way you're going to do that is, first thing you're going to do is you're going to get a good night's sleep. You're going to relax, and you're going to be very careful. You're going to have high levels of attention tomorrow. You're going to eliminate all of your careless errors. Okay. That will get you a whole bunch of points right away. I'm sure all of you guys have been taking practice tests, and the eliminating the careless error is the best thing you can do. So make sure you're deliberate. Again, be quick, but don't hurry. Don't rush so much that you're careless. You guys can do this, okay? This is what you've been working for all year long. This is exactly the moment you've been waiting for. So tomorrow morning when you get to school, you're going to be ready to go, and you're going to be ready for that exam. So some final thoughts, okay? First of all, congratulations. You know, it's been a crazy year. It's been a difficult year for students. It's been a difficult year for teachers. It's been a difficult year for everyone. And you guys have stuck it out. You've been trying to better yourselves all year long, trying to get through it to make sure that you guys could get credit on this exam. And you've taken calculus very seriously. I hope that we've helped to make the calculus exam viable for you guys. I hope that you guys are feeling confident. You're feeling strong about everything. I've got to take a moment. I've got to thank the awesome calculus team, Megan, Pooja, JP. You guys have been phenomenal, especially, you know, this evening with the difficulties I've had. I am so grateful that you guys and I got to work together. And you guys who are at home, thank you for being a part of our calculus family here at Fiveable. Whether you've been tuning in just for today, you've been with us the entire time. You know, it's been a great year, and I'm really looking forward to hearing how you guys do. So I think our time is just about up this evening. Like always, you know, follow us at Think Fiveable and all of our social media. We are going to now keep this conversation going. Our TAs are going to be available at Discord throughout the rest of the night. So please check in over there. But this is going to be the end for me. So thank you so much for tuning in tonight. I hope the cram has been a good review for you guys, and I wish you guys all of the best tomorrow. Best of luck. Again, good night's sleep tonight, and then go in tomorrow refreshed and focused, and just do what you know. You know, you've been working on this all year long, so all that practice is going to pay off. All right, you guys are awesome. Thanks for everything, and best of luck tomorrow. Take care, everyone.